ओके सर.
ओके, काय अडचण नाही.
पण चेहरा दिसतोय का?
हो हो, छान आहे, एकदम उत्कृष्ट आहे.
थोडं कॅमेरा असं करा.
पाठीमागनं थोडं फोकस ज्यादा आहे बा.
अधिक म्हणतोय ना. बर, 1 मिनिट. आता ती दरवाज्यात नाही ती लाईट थोडी.
आवाज येतोय ना क्लिअर सगळ्यांना?
आता बघा बरं सर.
हा, आता ओके एकदम.
राजू आहे का?
आहे.
राजू आता ठीक आहे का रे? राजू,
गुड मॉर्निंग नवले सर.
हा, गुड मॉर्निंग सर. गुड मॉर्निंग.
आवाज येतोय का क्लिअर व्यवस्थित?
हा, एकदम क्लिअर. घरी आहे कॉलेजवर आहे?
घरी आलोय.
बर बर, ठीक आहे.
मुलं वगैरे मध्ये येते म्हणून घरी.
Dr. Thombre, sir?
Yes, sir.
Now, please start at exactly at 10 o'clock.
Okay, sir. तुम्ही sir.
Over, sir.
Okay, sir. Yes,
Ready
sir.
आहे ना?
Oh, ready.
सूर्यवंशी sir, are you ready?
Yes, sir.
Sharp 10 वाजता चालू करूया.
Yes, sure, sir. No problem.
Okay, sir. नवले सर चालू करू का?
Yes, sir.
Okay.
Okay, sir. Now start it.
Very, very good morning to you all, my friends.
Recording in progress.
सांगोला तालुका शेतकरी शिक्षण प्रसारक मंडळ सांगोला, विज्ञान महाविद्यालय सांगोला, Department of Physics in collaboration with Internal Quality Assurance Cell IQAC organizes an international e-conference on recent trends in nanomaterials and its applications 2023. It is my pleasure to talk you through the conference, introduce you to the speakers and delegates that they have came from all over the country and also from other country to share their knowledge and enhance our mental horizon. Today's speaker and guest of honor, Dr. M.P. Suryavanshi sir. He came from University of New South Wales, Sydney. Mr. Mahesh Shinde, he is from California, USA. And chairperson of 4th and 5th session, Dr. R.A. Bugad and Dr. S.R. Kulal. Head of the department, Dr. B.B. Pale. Convener of the conference, Dr. J.V. Thombre, Ashok Kamble and all my colleagues. Foreign invitees and participants of the conference, my dear friends, ladies and gentlemen. I am immensely happy to welcome you all in second day of the e-conference and to Vidnyan Mahavidyalaya to the international conference on recent trends in nanomaterials and its applications. Dear friends, this is the first conference in the history of our college which is completely conducted on digital platform from last 3 years. This is possible only due to the efforts taken by our ex-student of physics department, stays their position as a professor and postdoc fellows in foreign countries. Now, I would like to introduce chairperson of today's first session of this international conference, Professor Ramesh Bugad. It is my pleasure to introduce Dr. Bugad. Dr. Bugad did his MSc from Shivaji University, Kolhapur, and PhD from Solapur University, Solapur. He is an associate professor at the Department of Physics, Sangola College, Sangola since 1993. He is awarded his PhD degree in physical sciences in the field of ferrite from Punyashlok Ahilyadevi Holkar, Solapur University, Solapur in 2021. His area of research includes the fabrication of thin film, lanthanum doped substituted MgZn ferrite, aluminum substituted cobalt ferrite, and aluminum substituted MgZn ferrite and copper nickel zinc ferrites. His group is credited with over 15 international journal publications and over 10 conference presentations. He has participated in some 49 different international and national conferences and seminars. He has worked as a chairperson in many international conferences. He has delivered plenty of guest lectures in all other colleges. He has written 4 books of physics and published by Aksharlena Prakashan. With this, I would like to conclude my speech by encouraging the delegates to participate with an increasing numbers in all the activities and discussions through these digital platforms for the whole day. I wish everyone a successful, safe and fruitful conference. And at the last, I invite Dr. Ramesh Bugad to chair the 4th session of this international conference. Thank you, sir. Thank you so much. Over to the Dr. Ramesh G. Bugad.
Okay, thank you, Dr. Shankar Dasare, sir. Very good morning, everybody. Welcome to 4th session of a international e-conference on recent trends in nanomaterial and its application, 2023. As a chairperson, I welcome to all delegates and speakers, which are coming from different regions. Firstly, I am very much thankful to convener and organizing committee of this conference for giving me opportunity for chairing this session. The research person of this session is Dr. Mahesh P. Suryavanshi, University of New South Wales, Sydney. It's my great pleasure to introduce today's speaker. He is currently working as lecturer in School of Photovoltaic and Renewable Energy Engineering, University of New South Wales, Sydney, Australia. He completed his BSc degree in 2008 in physics and MSc degree in physics in 2010 from Shivaji University, Kolhapur, India. He awarded PhD degree in physical science from Shivaji University, Kolhapur, India in year 2015. He appointed as a postdoctoral fellow SPRE, University of North South Wales, Sydney in the year 2019 to 2021. Brain Korea postdoctoral fellow CN University, South Korea during the year 2016 to 2019. He is honored with Discovery Early Career Research Award fellow from Australian Research Council in 2021. He is also honored with Early Career Research Award by the Ministry of Education, Research, Culture and Sports, Spain and European Commission in 2019. He received Best Presentation Award 7th Asian Pacific Forum on Renewable Energy from Busan, South Korea in 2018. He awarded Key Scientific Article Award from Renewable Energy Global Innovation Series, Canada in 2015. He received International Doctoral Exchange Student Scholarship, Korean Government in 2012. He received Eklavya Scholarship from Shivaji University, India in 2010. He awarded Undergraduate Student Award DKASC College, India in 2007. He granted patents for modified cellular approach presentation of a chalcogenide compounds for thin film solar cell. Another patent granted for green synthetic strategy for preparation of a colloid chalcogenide nanocrystal. Especially his research interest in earth abundant, environmentally friendly chalcogenide nanocrystal and thin films for solar energy conversion applications such as a thin film photovoltaic, agro PV, and solar fuels. Mainly his area of research includes the perovskite nanocrystal for energy application, mixed chalcogen and halogen compounds for energy application, nanostructure earth abundant transition metal oxides, hydroxides, oxyhydroxides, phosphoids and nitrides for electrolysis. He received more than $16 lakh grants for research in his project, fellowship and scholarship. In last 10 years, he has published 95 peer-reviewed journal articles, 1 book and 2 book chapters. His H index is 38 and I index is 74 and total citations are greater than 3,920 on Google Scholar. He delivered more than 10 keynotes, invited talk as a resource person. With this brief introduction of great person, Dr. M.P. Suryavanshi, I would like to welcome to deliver his talk. Thank you very much, sir. Thank you, Dr. M.P. Suryavanshi, sir.
Thank you so much, Dr. Bhugat, sir. This is a very long and very in-depth introduction. Thank you so much once again. Of course, I would like to also thank my classmate Jagannath Thomre, Dr. Jagannath Thomre now I should say, for inviting me to present my work in today's conference as well. Also, I would like to thank all the organizing committee members and Vidnyan Mahavidyalaya College for arranging this e-conference. I'm pretty sure, of course, I didn't get a time to attend yesterday's lectures, but I'm pretty sure that most of those lectures were helpful. And I hope today's my presentation will be also helpful for all of you guys. So let me share my screen and then I will present what we are doing at the University of New South Wales in the School of Photovoltaic and Renewable Energy Engineering. So, Dr. Jagannath, can you see my screen?
Yes, sir. It's visible.
Yes, thank
Yes.
you. Thank you, Dr. Jagannath. Anyway, so yeah, as again, I would like to thank Dr. Bhugat sir for a really a long and very in-depth introduction of mine. I never heard that kind of introduction before. I gave a couple of talks. So thank you again, sir. It is really my honor to come here and talk about what we are doing at UNSW. Again, Dr. Jagannath, thank you so much for inviting me. So let me get started and let you know, guys, what we are doing at the School of Photovoltaic and Renewable Energy Engineering. So as Dr. Bhugat sir introduced me, my name is Mahesh Suryavanshi. I'm an ASC DECRA fellow and lecturer. Lecturer here in Australia is also equivalent to the assistant professor in the School of Photovoltaic and Renewable Energy Engineering, University of New South Wales, Sydney, Australia. Today, I'm going to talk mainly about sustainable materials for a green hydrogen production. I think that's what the conference focuses on, sustainable nanomaterials and their applications. The schematic, you can see what we have done so far when it comes to the synthesis of nanomaterials and their application in sustainable or green hydrogen production. That's what we call it. Again, I would like to thank everyone for inviting me here. So mainly, my research group, of course, including me and my PhD students, my research assistants and postdoc, our research interests are mainly in the development of sustainable materials. Those are earth-abundant, non-toxic for different applications. One of them is a green hydrogen production, which is a very hot topic these days. But not included to only this one, but we also make these materials and study their applications in thin film solar cell, also solar windows as well as the agricultural photovoltaics, which is a kind of new field using the scalable approaches. So today, I will present what we have done so far in the development of the sustainable materials for a green hydrogen production and our contribution to this field using environmentally friendly, low cost, and easily preparable materials, which are already synthesized by using different scalable approaches or the methods you can say. So before I actually start my presentation, I would like to tell you briefly about my university, where it is located and what kind of different schools we do have. So give me 1 second. I think I'm having a trouble seeing my screen properly. Okay, I think this is better now. Okay, so UNSW has been established in 1949. So can you hear me, Jagannath?
Yes. Yes.
Okay. So UNSW has been established in 1949, and it ranks about 43 in the 2021 QS World University Ranking. Sorry, I didn't get time to update the ranking here. So it's in the 2022 ranking. It stands sixth in Australia, which is in the overall rankings, and the first in Australia for engineering and technology. So at UNSW, we have several different faculties, like 9 different faculties. Among them, there is a UNSW Engineering and UNSW Science faculties. That's what like where we belong to. But we do have a business faculties, and there are so many different ones. Also, out of these like 2 different faculties, my school is in the UNSW Engineering faculties, which has again different several school. Not going to talk in detail about each and every school, but I will mainly talk about my school, which is the School of Photovoltaic and Renewable Energy Engineering. I assume with its name, probably most of you guys must have got an idea about what should be the main thing that my school is doing. So it's all about the photovoltaics and renewable energy. And this is what I'm going to talk today about. Of course, my school, I don't know how many of you know about this school, but my school is one of the top school in the world, or I would say is only school in the world. When I say a school, it's the department. Just like back in India, we call it as a Department of Physics or Department of Chemistry. So here we call it as a school. So our school is one of the top school, or you can say it's only school in the world, which is recognized for its research in solar cell or photovoltaics. Our school has a state-of-art facilities for very high efficiency solar cell, which are not included to only silicon solar cell, but also thin film solar cell, which are emerging one. For example, copper indium gallium sulfide, as well as copper zinc tin sulfide, and also recently a perovskite solar cell, which is a kind of again a very hot topic. It's not only about we have a state-of-art facilities, but my school also holds world record efficiency for all of 3 generation of the solar cell technologies, which is silicon, and then thin film solar cell technologies, and again recently a perovskite solar cell. Of course, it's not only about my school. Maybe most of you have heard about the Professor Martin Green's name. People call him as a father of photovoltaics. So he is the main person who made a significant contribution in the School of Photovoltaic and Renewable Energy Engineering department. And because of his long time efforts of about more than 30 years, the silicon solar cell technology, or you can simply say solar cells, those we see outside on the rooftops or in the commercial buildings, it's all because of his efforts, which took about more than 30 years. So he's probably the main person from our school, and he's a well-known scientist, or I would say engineer, who has made a significant and major contribution in the silicon solar cell technology. And thanks to him, now the people like you and us or everyone are quite easily can afford these solar cell technologies to put it on our rooftops and then generate the electricity out of those. So yeah, this is the small and brief introduction about my school. There is a lot more that we are doing at my school. Not going to talk in today's presentation, but if I get a chance again in the future, I will again explain what else we are doing at my school, except what I'm going to show you today in my presentation. So anyway, so let's go ahead and get started about the actual presentation. Again, this is a quite common introduction. Most of you guys must have seen these kind of slides so many times about the global warming. So we all know our aggressive use of fossil fuels is responsible for increasing CO2 emissions, which accelerates the climate change, and thereby threatening the natural ecological balance as a consequences of this global warming, right? So therefore, there is a high need or urgency, or we must need to find a suitable alternative, sustainable energy sources or solutions to resolve the issues associated with the use of non-renewable energy sources such as fossil fuels. So this is the simple schematic where you can see what are the different drawbacks or how the global warming is affecting us in terms of our daily lives. It's not only to the human health, but it also to the animals living on the earth or land, or also inside the water. So again, raising the point is that there is a very urgent need to find out a suitable sustainable energy solutions to avoid these tackles in the long-term goal. Probably for my kids or for your kids or probably my grandkids as well. So yes, so what are these different renewable energy options? Of course, I think we have all studied about the different renewable energy sources that are available for us. But among those different renewable energy sources, we know that the solar energy is world's most abundant energy source, right? So a brief overview of these energy reserves available on Earth, which demonstrate the dominant position of the solar energy or the sun's energy among all non-renewable as well as renewable energy sources. So it has been studied that, or it has been reported that the total sum of the recoverable energies from all the resources is around 1% of the solar energy supplied to the Earth surface by the sun. Moreover, the solar energy, which is supplied to total Earth surface of the Earth, is nearly about 9,600 times larger than today's overall world's energy consumption. So we also know that enough sunlight reaches us or to the Earth's surface every 15 minutes to power the world for an entire year. Again, last but not least, this is a clean, safe energy source that powers home, offices, business, and power plants everywhere. However, the solar energy is much more than enough to meet all the energy needs for the lifetime of the solar spectrum or the solar system. But the real challenge lies in the actual development of economically viable technologies for its harnessing, also storage, and also its utilizations, right? So simply that means even though we have abundant of solar energy or sun's energy available for us to utilize, we don't have specific technologies or readily available technologies that can be used to harness the sun's energy in an efficient way and then store it and then utilize it. Not going to say that's 100% true now, because again, as I said earlier, because of Professor Martin Green's efforts, 30 years of efforts, now there are solar panels that are capable enough to harness the solar energy and convert it into the electricity. But the major problem with those solar cells is also that they can only absorb about 26 or let's say around 27% of the sun's energy and convert it into the electricity. But there is still a huge scope, or there is about more than 70% of the energy of the sun's energy that we are not utilizing, right? So what our job is what our job as a scientist or as an engineer is to find out these economically viable technologies for the better use of the sun's energy for our community. So how we can harness this solar energy, right? So that will be the main question that arises in front of us, right? So again, the solar energy can be used it can be used directly or indirectly in a variety of aspects, such as the solar thermal plants, as well as the photovoltaics that I have been mentioning since the starts of my presentation, and finally the artificial photosynthesis, or we also call it as solar fuel productions, right? So what are these different aspects and how they harness the solar energy? So I think about the solar thermal plants, I think I don't need to explain it quite a lot, because I think most of you at your houses or on the rooftop of your houses, you have this solar thermal plants, right? I wouldn't say it's a solar thermal plants, but you have the solar water heater, right? So that's nothing but the simple solar thermal plants. But the second one and the third one, which are quite interesting to me, and I'm going to talk a little bit more about that, is the photovoltaics and artificial photosynthesis technologies, right? So today, this PV represents the most widely disseminated technology and is one of the fastest growing technology or industries in the world. So this PV technology simply employs the solar cell or photovoltaics. So this is actually a photovoltaic panel, and you can see these small dots or small squares. These are nothing but the solar cell, and they have arranged it in a parallel or in series to improve the final output, either in terms of the voltage or in terms of the current density. So what is this PV technology? So this PV technology simply employs solar cells or solar PV arrays. So that's what I said, solar cell, and when we connect them in a series or parallel, we call them as a solar PV arrays. So to convert energy or sun's energy into electricity, which has an intrinsic difficulty in terms of storage, right? So when I say intrinsic difficulty in terms of storage, is that we all know that, right? The sun is only available in the daytime, but we don't have a sun at the night, right? So that's what the people call it as an intermittent nature of the sun's energy. It's available for particular time of the day, and then it's not available in particular time of the day, and the remaining time of the day. So considering that intermittent nature of the solar energy, converting this solar energy into easily storable chemical energy or fuel has emerged as another ideal option to utilize the solar energy. So among these different approaches, again, the hydrogen generated from this water splitting method or water splitting process, also people call it as artificial photosynthesis, has received a tremendous attention as the promising fuel, as the most promising fuel, especially for powering fuel cell vehicle. So I think artificial photosynthesis is the same method or the same process like a natural photosynthesis, but there is only slight difference. So what is this slight difference? So this artificial photosynthesis is a way of mimicking the natural process that our plants use to create the energy from sunlight, carbon dioxide, and water. So simply, this is a chemical process that converts the water and the carbon dioxide into oxygen, hydrogen, and carbohydrates, right? So this term, the artificial photosynthesis, is commonly used to refer any scheme or any process of capturing and storing the energy from the sunlight into the chemical bonds of a fuel or solar fuel, which is nothing but the hydrogen, right? So of this artificial photosynthesis process, I think solar or photoelectrochemical water splitting that converts the water into hydrogen and oxygen, which is a major topic of the research of this artificial photosynthesis process. So, of course, as I said, from my title, we are working on making a sustainable materials for solar energy conversion applications, right? But solar energy conversion applications are broad way. It's a broad concept, right? That means like we are also working on thin film solar cell producing hydrogen from the sun. But today in today's presentation, I will mainly only talk about how we are making these materials and how we are using them to produce the hydrogen using the sunlight. And probably in the future, if I get a chance again, then I will speak about how we are making the materials and then making the thin film solar cell out from those materials and then use it to convert the sun's energy into electricity. But today, I will mainly talk about how to make the materials and then use them in the application to produce the hydrogen from the sun's energy and the water. So the first question will be, why hydrogen, right? Simple, it's abundant, clean, and efficient energy source, and it can be derived by various means from the chemical compounds such as water and ammonia. So one of the most common ways to extract the hydrogen is with a device called as an electrolyzer. I'm pretty sure most of you have studied this in the probably sometime in your like a high school or senior college or junior college, somewhere around that time. So what this electrolyzer does? So this electrolyzer is nothing but the comprise of the different electrodes. We call it as one as anode and one as a cathode, and there is a membrane. So when you pass an electric current to this electrolyzer, put some immerse in the water, it splits water into hydrogen and oxygen at a cathode and anode respectively. And these two these two generated gases through the electrolysis process can be then stored for various uses. Of course, through electrolysis process, the products are generated is simply hydrogen and oxygen, right? And both of them are useful. Of course, the oxygen is not that useful through the electrolysis process, but it's generally useful for us. But in a electrolysis process, only the hydrogen is important. But the produced oxygen that usually goes into the air, and that helps us to have a sustainable environment around us. So again, this hydrogen is nothing but the energy storage medium, which is similar to battery, but unlike batteries, which eventually lose their ability to hold the charges, or simply the battery dies, this hydrogen gas can be stored independently. Perhaps I would say the base argument in the hydrogen favors is that when we burn the hydrogen for heat or to power the vehicles, to make the electricity, the only byproduct is nothing but the chemically pure water. So so from this one, you can understand why the hydrogen is very, very important in today's scenario or today's situation to even actually run the cars, because of the global warming or the pollutions that we are seeing all around us, right? So in addition to all above the mentioned advantages, I think the hydrogen can also help us in reducing the energy dependence as well as reduce the pollution. That's what I just said, and by reducing the carbon oxide emissions in the atmosphere. So yeah, so this is about why hydrogen. Now, interestingly, the hydrogen also has a different types. I wouldn't say different types, but it has been distinguished based on its color, which is kind of like very interesting when I started learning about the hydrogen. So this hydrogen is often associated with the different colors. It's whether gray hydrogen, blue hydrogen, or the green hydrogen. So these colors actually represents key distinctions or the key differences in the emission profiles for the various ways hydrogen is produced. So that means simply how hydrogen is produced defines its color. That probably you can see from the slides, right? It's pretty much clear. So first of all, this gray hydrogen is typically produced from a natural gas in a process called as a methane reformation. Again, I'm pretty sure we have all studied about methane reformations in our high school. While the brown hydrogen, which is also a subcategory of this green hydrogen, is produced from the coal gasification. So nothing but the production of the gray hydrogen from the oil by simply burning an oil and coal gives it a color as a gray hydrogen. I think you will understand why the people call it as a gray hydrogen probably in the next couple of slides. So this gray hydrogen, which is the most dominant and cheap method of producing hydrogen in the today's situation, but it actually accounts for the highest CO2 emission. Now you might understood why the people call it as a gray hydrogen, because it's simply right. We use the coal and we use the natural oil. For example, petrol and diesel. We use petrol and diesel to run our cars or vehicles, right? So when we use this natural oil, or let's say petrol and diesel in simple way, we run the cars, but our cars or the vehicles introduce the carbon dioxides, right? But in other way, we are using the same natural gas, natural oils or the gases and these coals. Instead of running our vehicles, we are using them in the methane reformation to produce the hydrogen. So that means we are producing hydrogen using the same way, near about the same way, but producing a hydrogen, which is also introducing the highest amount of the carbon dioxide emissions into the atmosphere. And that's the reason the people call it as a gray hydrogen. Same way, the blue hydrogen is also counted, but only difference between the gray hydrogen and the blue hydrogen is the way they produce it. But also, as you can see, the blue hydrogen is also produced from the natural gas using a process called as a carbon capture storage. Not gonna explain that in detail because I will mainly speak about how the green hydrogen is important and how we should produce a green hydrogen rather than the gray hydrogen or the blue hydrogen. That's because we are progressing towards the sustainable economy, and the important thing in achieving that particular economy is that we develop the technologies which are sustainably viable economically as well, but does not account for a highest amount of the CO2 emissions into the atmosphere, right? So, but again, from the slide, as you can see, the most of the contributions of the hydrogen production technology is either from the gray hydrogen or the blue hydrogen, and only about the 4% for a gray hydrogen, right? So how this gray hydrogen is produced, or why this is categorized as a green hydrogen? I'm like it has given a color as a green, right? Only because this hydrogen is produced using a variable renewable energy sources, such as solar, wind, via electrolysis of water. That's what I explained in my previous slide, right? Producing a hydrogen is easy, not that difficult, but the way you produce it, that matters a lot. So when we produce the green hydrogen using the renewable energy sources, which is simply nothing but the solar cell or the photovoltaic system or sunlight, or we can also use the windmills or the windmills to generate the electricity and use that electricity and give it to the electrolyzer to produce the hydrogen, which will be then accounted as a green hydrogen. So this production of the green hydrogen process is simply clean, but currently very expensive. I will tell you why this is very expensive in next few of my slides. But again, when we say the producing the green hydrogen is very expensive, at the same time, the cost of the renewable energy sources have decreased quite a lot in the recent year, especially for solar PV in particular, right? So the costs associated with these are a function of the electrolyzer costs and the cost of the energy sources. As of today, as I said, only 4% of the hydrogen is recently produced through the electrolysis, which is compared to the blue and gray hydrogen is really very less. The reason, because probably the technologies available, renewable technologies available to us, which is either solar or the windmill, is currently very expensive rather than the methane reformation or carbon capture storage processes, and that's the reason the percentage for the green hydrogen is really very low in today's scenario. So what we need to do is we need to work on how we can improve this percentage by working on improving the efficiency of the electrolyzer, reducing their cost, also simultaneously working on the improving the efficiencies and the lowering the cost of the renewable energy technologies such as the solar PV and as well as the wind energy related technologies as well. So again, like as I said, like mainly the presentation will be focused on how we can produce the green hydrogen, because the blue hydrogen and the gray hydrogen, the technologies has already been commercialized and they are already in the market. But again, they account for the highest CO2 emissions into the atmosphere. So that's the reason we need to work on producing a green hydrogen using sustainable technologies or renewable technologies. So how this green hydrogen is produced using a different way. Of course, there are so many different techniques that we can use to produce a green hydrogen, but not going to talk too much in detail about this one, because I will mainly speak about solar hydrogen production because it's already been 25 minutes since I started my presentation. So of course, there are different ways like a direct solar water spreading, which today I'm going to talk a lot more about. And there are different ways like biomass, solar PV, wind, and geothermal. So what happens with these four, I will briefly tell you. So whatever electricity we generate, either by biomass degradation or from the solar PV, wind, and geothermal, that we use as an input to the electrolyzer, where we place some electrodes into the water and then we generate hydrogen as output. But in a direct solar water spreading, this is not the way. What we do is in direct solar water spreading, we prepare materials which has an ability to absorb the sunlight directly. And then when we put them in the water, they absorb the sunlight, produces the electron hole pairs, and then produce the electron hole pairs, separates via junction formation, and then produce electron or separated electron, then contributes in the formation of the hydrogen at the cathode side and the oxygen at the anode side. Again, you will see that in my next few slides. So this is what about the biomass production, like hydrogen production using a biomass. I think this is well known for each of us. So I will just keep this slide. this is the hydrogen production using the electrolysis. This is what I was explaining in my previous slides. So the electricity, so of course, this is what they say, the surplus electricity. That means, let's say we have a solar PV farm or the wind farm or geothermal plants. Whatever the surplus electricity we generate from these all three plants, we use that extra energy or the extra electricity to power these electrolyzers to produce the hydrogen. So that means it's a two-way benefits. We are using these all three farms to generate the electricity to power the houses, businesses, and the commercial complexes. But whatever the extra electricity that we are producing from these three technologies, that can be used to power the electrolyzer or as an input to the electrolyzer to produce the hydrogen. So we can use this all to simultaneously produce the electricity to power the houses and also simultaneously producing the hydrogen to run the fuel cell vehicles. Okay, so this is the kind of interesting one that we are working in the lab, which is nothing but the direct PEC water spreading, and also people call it as a PEC or photoelectrochemical water spreading. So the techno-economic, the PEC approach to generate the hydrogen can compete with the PV coupled electrolysis, which is nothing but the previous one, or even with the steam repumping of methane, which is nothing but the process to produce the gray hydrogen, if we meet certain efficiency and the stability metrics. So when I say stability and the efficiencies, you will understand what is the current state of art of this direct PEC water splitting technologies in terms of its efficiency and stability, which is far below or far behind the electrolysis, PV electrolysis, and the steam methane reformation technologies. So simply how this hydrogen is produced using the PEC water spreading. So these are simply schematic of the electrode system. So this is a thin film electrode system and this is a particle system. Only difference is that we prepare a thin films of energy absorbing materials and then put it in the electrolyte or simply water, shine a light, and then there will be the production of the hydrogen and oxygen. But in the particle system, you don't need to prepare electrolyte. What you need to do is you only need to prepare the photocatalyst, which is a kind of like particle suspension or the slurry, that's what we call, and then just dilute that concentration or the particle or photocatalyst slurry with a water and ethanol mixture and just shine a light on them. And this photocatalyst slurry will produce hydrogen if it is a photocathode, and this will produce oxygen if it is a photoanode. I mean, like it's a p-type or n-type symbol. So yeah, so simply only thing that I want to emphasize, we are mainly working on the electrode system because that's what our expertise is, like making the thin films and then using them in either thin film solar cell or solar fuel production. So, and this is what the people call it as a PEC water spreading. This technology, the people call it as a photocatalytic water spreading. So how this PEC water splitting cells work, or simply PEC cell works, simple schematic. There is a one photoanode, there is one photocathode. Based on their electrical conductivity, we distinguish them in two different systems, photoelectric systems. If it is N-type, then it is a photoanode. If it is a P-type, it's a photocathode. So we have different options in choosing the photoanode and photocathode. Even though we have different options, I think most of them, there is a trade-off relations between the efficiency and the stability. You will see that in the next slides and how we are trying to overcome them. So simply how this PEC cell works. So when semiconductor, either photoanode or photocathode, absorbs the sun's energy, the electrons and holes are generated. It's the same way the solar cell works. The only difference will be how this electron and the hole pairs will contribute in the oxygen evaluation reaction and the hydrogen evaluation reaction. So these photogenerated carriers can drive the reduction and oxidation reactions if the charge injection into the reactants are thermodynamically favorable. So again, probably when I say the thermodynamically favorable, then we need to look for their energy band alignments that should match with the this particular potential into the energy scale bar. If that matches quite well, then there will be a charge injections happen into this water splitting reaction. So when this happens, when this reaction is thermodynamically favorable, the reduction of the water to the hydrogen and oxidation of the reduced redox mediators occur on these photoelectrodes, either photoanode or photocathode, either at the photoanode, which is oxidation reaction, and the photocathode and the which is hydrogen evaluation reaction. So what does that mean in the short, like a simple way? So there is absorption of a light near the surface of the photoelectrodes, which is a semiconductor. Again, same either photoanode or photocathode. And there is electron hole pair generation. So the holes, which are the minority carriers, dip to the surface of the semiconductors, that's in a P-type semiconductor, where they react with water to produce the oxygen. Sorry, in a N-type semiconductor, holes are the minority charges. So they dipped across and then they reduce the water or they oxidize the water to produce the oxygen at the photoanode. While the electrons, which are the majority carriers, are conducted to the metal electrode, that is platinum or any other semiconductor materials, where they combine with the H plus ions in the electrolyte solution to make the hydrogen on the P-type photocathode. Again, the transport of the H plus cations or the ions, not a cation, sorry, the transport of these H plus ions from the anode to cathode, which is this process, through the electrolyte, completes these overall electrochemical reactions or completes the electrochemical circuit. And that's how we generate the hydrogen and oxygen on these photoelectrode systems. Again, I guess, like I assume most of you know that to produce the hydrogen via photoelectrolysis or even the electrolysis, we need a potential of about 1.23, which is the theoretical value. But in reality, this value can be significantly higher, which is about 1.5 to 1.6 volt to split the water into oxygen and hydrogen. And this is our job, or as scientists or engineers, this is our job to achieve that theoretical value to split the water. So this is about the how PEC cell works. But when we fabricate the PEC cell, the main important thing in the PEC cell is the different photoelectrode materials, which is photocathode and photoanode, and they have different requirements. First one, to have a high efficiency of the photoelectrode, their band gap energy should match, and it should be at least 1.6 to 1.7 electron hole. It should be 1.6 to 1.7 electron hole, but not over 2.2 electron hole, because I think, again, we know that this is the optimal range where we can harvest the maximum of the sun's energy. Again, it should be a small enough to absorb the most of the sunlight, and that's what this value represents. Second one is materials durability. So that means because we prepare this material and we directly immerse them in the alkaline solutions, like a water solution, they should be very, very stable under this solution, also under illumination, because we have to shine a light for water splitting reactions to happen. So these two requirements should be met at the same time to have an efficient water splitting reaction. So what are the materials that are like capable enough to initiate this water splitting reaction? Of course, there are several oxides. Also, there are several nitrates and sulfide semiconductors, which can be used as a photocathode or a photoanode for water splitting reactions. But only the oxides are quite stable in the electrolytes. However, you will not find any oxide photocathode or photoanode which has a band gap energy of about 1.6 or 1.7 electron volt. On the other side, we have several nitride and sulfide semiconductors in the band gap range of this one, but they are not stable in these aqueous conditions. So what my point is that we have materials available in the literature, but there is a trade-off relation between these materials' performances. So one material is stable in the aqueous electrolyte, but its band gap is not that great to absorb the maximum of sunlight. However, other materials have a suitable optical band gap energy to absorb the maximum of sunlight, but they are not stable. So this is the research gap in this current field, and this is where we need to work on. We need to find out the suitable materials. They are suitable materials who possesses this optical band gap energy between this range, but simultaneously they are stable in the aqueous electrolytes, and that's what we are trying to do, or we have done so far, which I will show you in my next few slides. So again, I said, this is what we are trying to do. What we are doing is we are trying to improve the performance of these TiO2 nanorods arrays. The reason, because the TiO2 nanorods arrays, it has been demonstrated as one of the efficient photoanode material for hydrogen water splitting reactions. However, as I said, the band gap of TiO2 is very, very high, which is about 3.2 electron volt. So it does not absorb the maximum of the sunlight. So when I say the maximum sunlight is nothing but the visible region, but if you see the TiO2, its band gap energy is about 3 electron volt, that means it's only absorbed in the UV region of the sun spectrum, right? So what we are trying to do is we are trying to use the stability benefits of the TiO2 while adding several different materials on the top of TiO2 to absorb the maximum of the sun's light. And this is what I will present in my next few slides. And then I will probably wrap up my presentation because I only got less than 10 minutes. Okay. So how to improve the photoactivity? As I said, this is what we have done so far, and this is what we are trying to do. How we can improve the performance of the TiO2 or simply photoactivity is that when we grow TiO2, mostly using a hydrothermal method, there are some surface trap sites, or simply you can call it as a dipex formations on the surface of the TiO2, which actually act as the electron recomposition centers, or simply electron eating centers or killing centers that we need to be like a passivate. So once you passivate those surface traps, probably this schematics might be clear to you to understand that concept. So if we passivate those surface trap sites or surface defects, then we might get more and more generated electrons for the water splitting reaction to proceed. So how we can passivate this? By simply putting another metal oxide layer on the top of TiO2, or probably simply putting the silver on the top of TiO2, which is a noble metal, also plasmonic metals, or making heterostructures of the rutile TiO2 phase with anodized phase. This is one way we can improve the performance of TiO2. As I said again, band gap of this one, by putting these different heterostructures, will not improve. Okay, so what we need to do is we need to utilize the visible spectrum or the visible range of the sun spectrum, and that can be only done by either doping the non-metals, which reduces the band gap of this TiO2, which is nothing but nitrogen, sulfur, and the carbon, or we can do the chemical modification of TiO2 with the tungsten metals or the noble metals, such as the silver and gold, because silver and gold are plasmonic metals, noble metals, which absorbs in the visible region, or the interesting one, which is a sensitization of the quantum dots, either cadmium sulfide, cadmium selenide, or some other non-toxic elements. So this particular one that we are very interested in, and that's what we like doing it, because these all like quantum dots can be tuned to absorb the different wavelengths of the sun spectrum. So I will show you how we have made these kind of different quantum dots as a sensitizers on the TiO2. So these are the different approaches that we have used to improve the performance of TiO2. First one is nothing but the nanoparticle sensitizations, which is nothing but the quantum dot sensitization of copper, zinc, tin, sulfur quantum dots, because this compound has a band gap energy of 1.5 electron volt, and very famous for a thin film solar cell application. So that means it has also capability to absorb the maximum sunlight and can be used for hydrogen production. Also, as I said in my previous slide, non-metal doping, because doping the sulfur into TiO2 nanorods arrays will add additional energy levels into the TiO2 band energy that will reduce the band gap of the TiO2 to absorb slightly in the visible range of the sun spectrum. And finally, combining both of these strategies together to have like a double impact or synergistic impact on the performances. So this is a simple research design that we have done, like a sulfur doping, how we have done it, and then CCTS nanoparticle sensitization, how we have done it. Not going to explain in detail how we have done those. Like it's a simply these papers have already been published. So probably if you want to take a in detail look, they are all available online, or I can provide it in the chat later. So what we have done is, little bit about the methods. What we have done is we have simply grown the TiO2 nanorods arrays using the hydrothermal method on a FTO substrate. And then what else we have done is we have used a modified Cellar method, which I developed during my PhD for this particular compound, copper, zinc, tin, sulfur. And then we use this method to sensitize these small quantum dots of the CZTS nanoparticles on sulfur doped TiO2 nanorod arrays. So how we have done the sulfur doping is simply nothing but we took this TiO2 nanorod arrays grown on FTO substrate, and then we simply treated this FTO substrate in a annealing furnace in a sulfur atmosphere somewhere at around 300 degrees Celsius for probably 1 hour to dope the sulfur into these TiO2 lattices. And then finally, we use this modified cellular method to sensitize the quantum dots on the TiO2. So once we have done those, we tested the performances of this whole system for water splitting reaction. And then we achieved that though TiO2 gives us a kind of like decent photoelectric current density, the current density is relatively low compared to all other samples. But interestingly, when you employ or when you sensitize the CZTS nanoparticles on sulfur-doped TiO2 nanorods, the current density is very, very high, which is about 10 milliampere per centimeter square. Not going to emphasize on the current density values here. There's a different standards to consider the current density, but what my point is that when you use the two different strategies on the TiO2 nanorods, there is a high chance that we can improve the current density almost more than double. So you can simply see here, current density of the TiO2 is about 0.79 milliampere, but when you use the CZTS and the sulfur doping in TiO2, that goes to about 8.8 milliampere per centimeter square, which is very, very high. However, the problem is when you test the stability of this whole photoelectrode system in the water, you can see there is about 20% drop in the current density, initial current density, immediately after 2 hours. So you can imagine if we keep these photoelectrodes in a water system to produce the hydrogen under a sunlight, immediately after 2 hours, the photocurrent density is reduced to 20, like almost 20% drop, right? So that means if you keep going or keep performing this water splitting reaction, let's say for 10 hours, then the current density will drastically drop to almost zero. And then there will be no more water splitting reaction will happen on the photoelectrode surface. That's the one drawback of these chalcogenide compounds. But I will explain you how we have overcome the stability issues of this one in again my next few slides. Of course, simple different characterizations and measurements to confirm the high photocurrent density from this one and how much hydrogen and oxygen is produced using this method. A little bit of the detailed studies on like how this system is important. I will just simply skip it. We are running out of time. Again, this one as well, I will skip that. So simply what happens a little bit in short. So when we sensitize the CZTS on TiO2, you can see there is a type 2 heterostructure formation between TiO2 and the CZTS. In that way, there is a efficient transfer of the electrons generated in the CZTS to the constituent band of the TiO2, and then that helps to produce the hydrogen and the oxygen. But when you use the sulfur-doped TiO2 and then sensitize CZTS on the TiO2, what happens? As I said earlier, when you dope the when you dope the sulfur into TiO2, there is a formation of the additional energy bands in the TiO2 band energy levels. So that actually helps us to reduce this energy barrier between or reduce the distance required for the whole transfer from the valence band H or valence band of the TiO2 to the valence band of the CZTS, where the oxygen evolution reaction will happen. And that's how when you like minimize the distance or when you minimize the energy required to transfer this whole from here to here is like a kind of like a nice one compared to this system. And that's the reason the performance of this system is relatively higher than the CZTS TiO2 nanorods arrays compared to this one. Also, in another work, maybe I will skip this one. We are actually running out of time. There are a couple of works that we have done. So I will simply show you, okay, this system. So in one of the work, what we have done is, so for this work, so you must have seen the, if you take a clear look on the in this schematic, you will understand what we have done is we have prepared one of the electrode which acts as a N-type photoelectrode or N-type photoanode, where there will be only oxygen evolution reaction, right? But if you see on the right side where the hydrogen will produce, it's still platinum, right? So that means if we develop the system for large-scale commercialization, we again need to consider about the platinum cost. So which will again doubt the feasibility issues of this our system. So what we have done in another work is that we have replaced this platinum as well with another semiconductor because the platinum is very expensive. And we have formed the two electrode system to to produce the hydrogen and oxygen without any additional bias. And that's what I want to show you in this particular slide. So what we have done is we have prepared some quantum dots of this copper antimony sulfide, and then we have sensitized these quantum copper antimony sulfide quantum dots on nickel oxide nanosheets, and again on TiO2 nanorod arrays as a p-type photocathode and as a n-type photoanode. And then we have fabricated this two photoelectrode system to produce the hydrogen and oxygen without applying any additional bias. So what does that mean? We have only prepared this two electrode system, and we shine the light on that particular system, and we were able to see the production of the hydrogen and oxygen on a photocathode and photoanode respectively, with a produced current density of about 0.9 milliampere per centimeter square, and the solar to hydrogen conversion efficiency about 0.23%, which was one of the highest and recorded conversion efficiency for this kind of photoelectrode system that we achieved in 2018. Of course, this has been already improved by another group, but my point is to just raise the benefits of having this kind of two electrode system to produce the hydrogen without using any external potential. Okay, so again, just another one quick one. So if you see, again, these are the chalcogenide compounds, chalcogenide semiconductors. So if you see the stability, again, it's only stable, unlike the performance goes down immediately after 1 hour of reaction, right? So that means even though we have demonstrated this kind of system, the photoelectrodes are still not so stable in the aqueous electrolyte. So what we have done is we have come up with an idea to improve the stability of these semiconductor materials. Either it can be TiO2, Ap2O3, or the chalcogenides, by putting an additional catalyst on the top of this semiconductor system. So there are 2 points, 2 benefits of putting the catalyst on the top of the semiconductor materials. First one is the catalyst actually accelerate the water splitting reactions. It can be either PEC, HER, or a electrochemical OER, or PEC OER, or HER as well. While also simultaneously the protect your underlying semiconductor materials from degradation in the aqueous condition. So this is one of the catalysts that we have prepared based on the iron manganese oxide nanosheets using the electrolysis deposition approach, which is simply this one, nothing but. So what you have to do is simply take the precursors and the complexing agent, prepare the aqueous solution of it, and then simply put your electrode into it. And then after 10 minutes of reaction, you will see the catalyst has already been grown on any conducting substrate. So it can be either FTO, nickel chrome, or any other conducting substrate. But simultaneously, it can be also deposited on any semiconductor materials as well, like a metal oxide or chalcogenides. So ACM images, you can see nice formation of nanosheets and on a FTO substrate. But when you grow them on Ap2O3 nanorods, you can see there is a core shell formation of the nanosheets and the nanorod underneath. So the point is, when you test these photoelectrodes or photoanode in the water splitting reaction, you can see this bare Ap2O3 gives a current density of about 0.93 milliampere. But when you put this catalyst on the top of it, it improves the current density almost 3.5 milliampere, 3.4 milliampere per centimeter square, which is kind of like a huge improvement. However, the interesting point is that if you see the stability, even after 8 hours of a water splitting reaction, you can see barely there is any decrement in the photocurrent density, which demonstrate the importance of having a catalyst on the top of the semiconductor materials for water splitting reaction. Also, again, what we have done, we have used this kind of like a different catalyst, which is nickel iron based catalyst. And then we have put it on the TiO2 nanorod arrays. And we have seen that this catalyst is much more stable than the previous one, with the stability over 24 hours without any noticeable degradation, and the improvement in the current density from about 0.71 milliampere to 3.85 milliampere per centimeter square, which is a kind of like a very, very good results. And this paper has already been published in the JMCA, this one in the A-series catalysis, and it has been highly cited because of its simple demonstration of this electrolysis deposition approach to grow this catalyst. And a lot of other researchers all over the world has used this my developed electrodeposition approach to prepare a variety of different catalysts, and have published a paper in Nature series journals or even in the science journals. So that demonstrates the effectiveness of the electrolysis deposition method to produce the electrocatalyst, and also use this electrocatalyst on the top of any semiconductor materials to protect them and also improve their performances. So finally, summary. Of course, we have shown. I mean, like we have worked quite a lot on improving the performance of TiO2 by using a different approaches like metal, non-metal doping, and the visible light absorbing nanoparticle sensitizations. Also, we have shown the demonstration or the synthesis of these copper chalcogen and nanocrystals using vegetable oil-based solvents as well as deputytic-based solvents. And also, we have demonstrated a scalable room temperature electrolysis deposition method to produce the catalyst on any kind of material or any kind of substrate, and have tested their application in a photoelectrical water splitting systems. Finally, these are some new directions that we are working on. So as you have seen throughout my whole presentation, like these chalcogen compounds are good one to improve the performances, but their stability is not that great in the aqueous conditions. So what are different options we have rather than putting the catalyst? So there are a few different options that we have where we don't need an additional overlayers such as the catalyst layer to improve their stability. Of course, it's always better to put the catalyst on the top of the semiconductor materials so that we can accelerate the water splitting reactions. But if your semiconductor material itself is a good photoabsorber and itself has a good stability, then we will have additional benefits from those compounds. So what we have done is like we are working on developing this new class of compounds, which are the chalco halides. And we have recently published a paper in Chemical Reviews on this particular topic, which has a chapter about 72. In another work, what we have done is we have overviewed different photoelectrodes for this hydrogen production method using the solar water splitting technique. So we have actually covered all the different photoelectrodes, either photoanode or photocathode, and wrote over 100 pages of the article, which has published in this Progress in Material Science, which again has an impact factor of about 48 or 49. So I would request you to go and read this paper so that you can get some idea on how you can further improve or contribute to this particular field of technologies. Also, we are also working on developing this zinc-based nitride materials. The reason because nitride materials have been predicted as a very efficient one and as an effective alternative for this chalcogenide or chalco-alloy materials, considering their stability and band gap energy and the electrical conductivity and also defect tolerance. So we have also got some grants to develop these materials with Professor Martin Green that we are working on. So with this, I would like to finally conclude my presentation by acknowledging my mentors, Martin Green, Professor Xiaojing Hao, and Professor Rosamund, and my collaborators, of course, my PhD students and my REs, those who helped me to get those data and detailed studies on those catalysts. Also my collaborators at UNSW and ISC, Oxford, and the Chatham National University. Finally, I would like to thank UNSW Sydney for giving me a chance to work here as a lecturer, and also the Australian Research Council for awarding me with a Discovery Early Career Researcher Award. That helped me to actually initiate my career as an independent researcher. And also I would like to thank Ministry of Spanish and partially to European Commission for awarding me with the Early Career Researcher Award in 2019. Finally, thank you so much for listening. I would be very, very happy to answer any of the questions that you have in your mind. Thank you.
Thank you very much, Dr. M.P. Suryavanshi sir, for a nice lecture on sustainable material for green hydrogen production. Now this session is open for discussion. If participants have any question, they can ask her.
Hello, am I audible?
Yes, Ketan.
Nice to see you, Mahesh, after a long time.
Nice to see you too, Ketan.
Yeah, it was a wonderful and fruitful session.
Thank you.
I'm having a couple of questions. One regarding photovoltaic cell, solar cell. can we use the entire electromagnetic spectrum coming from the star sun to harvest, means to convert energy with the help of solar cell? Means suppose we put the solar cell outside the Earth's atmosphere. So is it possible to utilize entire electromagnetic spectrum or no?
Yes, I'm like, you don't need to go out of the Earth atmosphere. I think that's also possible to do it here as well. So as you can see in this presentation, I'm like on this slide. So what we have tried to do here, as I said, like TiO2 only absorbs in the visible region of the light, right? Sun spectrum. So we can build a tandem cell. So when I say a tandem cell, it's like one material has a different bandgap energy, another one has a different bandgap energy, and another one has a different bandgap energy, right? So in this case, TiO2 has a wide bandgap energy. That means this will only absorb in the UV region, okay? And then you put the low bandgap energy material on the top of it. So let's say it's a 1.5 electron hole, which absorbs mainly in the visible region. So I'm like, in this work, what we have done is we have only considered these two, but people have already gone a little bit up, and they have done it as like, they have fabricated a multi-junctional solar cell where they have used wide bandgap, wide bandgap, mid bandgap, and narrow bandgap. So it's kind of like a UV absorbing material, visible absorbing material, and the near absorbing material. So that way we can actually cover the entire spectrum. Easy. Yeah, it's easy, but it's a kind of like a very difficult job, because when you put all three different materials on the top of each other, then there is a high chance that there will be interface recombinations might happen quite significantly. So that will impact on the final performances. But there is already the PV technology available in the market, which people call it as a 3PU technology. But because of its cost, they are only applicable to use in the space photovoltaics.
And the next question is, when you say hydrogen production, so is it hydrogen cation or hydrogen molecule?
No, it's a hydrogen gas.
H2.
Yeah, it's a pure H2 gas. So the purity of the H2 gas that we have tested, probably somewhere here. Yeah, in here. It's almost about like a 96 to 97%. It's a high purity H2 that we were able to produce.
Okay. Thank you.
Because it's in the gas form, they are easy to collect. But the problem with this technology is that because we simultaneously produce the gas, like hydrogen on the photocathode and the oxygen on the photoanode, right? So this stays in the one electrolyzer together. So if you don't collect the hydrogen gas quite well, then there is a high chance that there is a crossover of this produced hydrogen on one side and oxygen on the other side, and the formation of the very, very explosive mixture, which is nothing but the H2 and O2. And I think there have already been a couple of incidents reported all over the world because of this one. So even though hydrogen is good for the future, I think we need to really look for the better ways how we can collect this produced hydrogen very efficiently and without any problem.
Oh, good. So thank you.
Yes. Thank you, Ketan, for nice questions. Dr. Jagannath, any questions from your side?
No, participants will ask questions.
Any question? Now, any question from participants? Now, conclude this session. A very nice lecture delivered by Dr. Mahesh P. Salunke sir on topic sustainable material for green hydrogen production. Now, world energy consumption is increased abundantly. How solar energy is effective to avoid global warming and sustainable economy. In his lecture, he explained on PSC water splitting cell works. How PSC water splitting cell works. Now, also he explained the production method of a green hydrogen for sustainable technology. Dr. M.P. Suryavanshi sir explained how water that can be splitted for green hydrogen and oxygen. Now, he not explained only this splitting of a water for green hydrogen, but also he explained a photo activity by TI2 photo anode. Now, the information given by Dr. Mahesh P. Suryavanshi sir is useful for researcher and budding scientist. I would like to conclude this session. I am very much thankful to participants for their silenceful listening. Okay, thank you very much. Thank you very much. Dr. Dasari
Thank
sir.
you so much, Dr. Bhugat sir. Also, thank you to Dr. Dasari sir, and also thank you finally to Dr. Jagannath sir. I will leave the meeting because I got another meeting from my with my colleagues. So, but happy to see here again, everyone.
Okay, thank you,
so
sir.
Thank you again.
Thank you.
Bye bye.
Okay, thank you, sir. It is my pleasure that I am here for vote of thanks now. On behalf of my college and organizer of this international conference, I am very much grateful and thankful to my friend Dr. Bhugat for chairing this very nice session. It is our great honor that we are here with the eminent personality like esteemed Professor Dr. M.P. Suryavanshi. I am very much grateful to Professor M.P. Suryavanshi for his excellent and nice presentation. He came from Sydney and he has given an excellent time for this conference. I am grateful and very much thankful for his nice, excellent and valuable presentation. Now, I would like to conclude and hand over the session to Dr. J.V. Thomre.
Thank you, sir. Now we will start session 5th. Once again, I welcome all in session 5th. In session 5th, we have resource person Dr. Mahesh Shinde from 12 Benefit Corporation, California, USA, and the chairperson of the session is Dr. S.R. Kulal. Dr. S.R. Kulal is working as assistant professor in chemistry at Raja Ramrao Mahavidyalaya, Jat. He has completed his BSc and MSc from Shivaji University, Kolhapur. He received his PhD degree from Shivaji University, Kolhapur, and title of PhD thesis is Synthesis and Structural Characterization of Mixed Metal Oxides containing transition metals and lanthanide ions. Since June 2012, he is working as assistant professor in chemistry at Raja Ramrao Mahavidyalaya. Currently, he has responsibilities as IQAC coordinator, PG coordinator, nodal officer of MIS, NIRF, AISHE, and Atal ranking. Dr. Kulal is having a teaching experience of 18 years. His area of research interest is in catalysis and superhydrophobic materials. Under his supervision, 4 students are working for doctoral studies. He has successfully completed minor research project funded by Shivaji University, Kolhapur. He has published 30 research articles in well-reputed international journals. He has delivered 10 invited talks at various conferences and seminars. With this brief introduction, I welcome Dr. S.R. Kulal sir. Dr. S.R. Kulal sir, it's over to you. Thank you.
Okay, thank you, Thomre sir. You have given, or the college have given me opportunity to work as a chairperson for the session of that 4th May 2023 in the International E-Conference on Recent Trends in Nano-Materials and Its Applications, that is RTNA 2023. I will introduce the resource person of this session, Dr. Mahesh A. Shinde. Currently, he is working as a senior formulation engineering, 12 Berkeley, California, USA. His area of research interest is large area fabrication, optimization, and characterization of transparent conducting electrodes for flexible and bendable electronic devices, including electrochromic device, formation and optimization of characterization of low temperature pressurable metal oxide semiconductors like NiO, WO3, zinc oxide in various solvents. His experience of the research work is senior formulation engineer, 12 Berkeley, California, USA from December 2022. His research experience, postdoctoral researchers, material sciences and engineering, North Carolina State University, February 2022, December 2022. Postdoctoral researcher as Yungdam University, South Korea from September 2021 to January 2022. His PhD work, he has completed his PhD work in Incheon University, South Korea on the topic flexible electrochromic devices with highly stable silver nanowire based transparent conducting electrodes. He has completed having the educational career. He has completed PhD in Incheon, South Korea. He has completed his BE in Mechanical Engineering 2012 in KIT Kanpur and MTech in Mechanical Design in 2016 in RIT Sangli. Materials synthesis and processes and characterization technique used: coating, slot die coating, wire bar coating. Synthesis technique, he has carried out the work by the technique Sol-Gel method and hydrothermal method. He has reviewed number of articles, in totally 18 number of articles he has reviewed. He has attended the number of conferences, 3 and delivered talk in 3 conferences. This is the brief introduction of the resource person of this session. I welcome to Dr. Mahesh Shinde sir. Please start your session, whatever you allocate the topic. Thank you.
Hello, Kulal sir.
Yes, sir.
As the head of physics department, I again wish to welcome to you. Sir, again I wish to welcome our resource person, that is Mahesh Shinde. And also especially I wish to welcome to you, sir, because you to take best time, valuable time your to the attendance. Okay, sir.
Okay,
now start this session, sir.
Okay, good morning, everyone. It's really nice to having here and show my research experience to everyone. Can you listen? Is everybody can listen to me?
Yes, sir.
I will share my screen now. So I will just present my small for my PhD area. So currently I'm working as a formulation engineer in the organization. So this is my introduction. Is you know my name and my hometown is Shetkari, and currently I'm in India. So currently I'm in Shetkari. So I did my education in the master's and bachelor's in India. So I did my mechanical engineering collaboration technology in Kolhapur and master's in RIT, and I did my PhD from 2007 from Nano-Materials in Korea. So after the PhD, I did my postdoctoral at small finance in Korea in the same lab. After that, I moved to the USA for my postdoc.
Hello, Dr. Shinde sir, your voice is breaking.
Okay. Network problems here, so I'll just make. Okay, can you? Is everybody can listen me now? Hello.
Yes, sir. Yes.
Okay. So I had like 2 postdoctoral experience. One is from Nano-Materials, South Korea, and one is from USA. After that, I moved to like industry, like organization from December 22. So just I will start my research presentation. This is like a small part of my PhD experiment. So my PhD thesis title is flexible electronic devices with highly stable silver nanowire transport electrode. But the smart window. Smart window is window which can just so in future, like in the windows, we don't need to use the curtain. So this window we can control the sun transmitters by adjusting its color. So you can see this in the schematic. It's a bright mode. So if you want the full sunlight, so you can get the full sunlight. But if you don't want the sunlight, we can just turn this like coloration and we can get a small part of sunlight. So in future, this is like in the in commercial in the US now, all like companies that they are industries, they are in the smart windows. With this smart window, we can reduce energy losses and we don't need to use air conditioning in the future. So the smart window has three major parts. One is like electronic material. The main part to change the color of the window with the tungsten oxide is the best electronic material we have, and this is, we still don't have any alphabet for it. So I'm considering for our experiment, I use that as a material. Another part is transfer conducting electrode. So we in every device we need a conducting electrode to transfer the charge. And third is electrolyte, the ion resistance. This is we can see the structure of the smart window. Currently, my basically topic is related to the electrode. So tungsten is the best material, so I'm not working on that. And electrode is like already researched on it. So main part my research is concentrated on the transparent conductive electrode. So transparent conductive electrode is a thin film which is optically transparent. And depending on its sheet resistance means
Hello.
how much it's conducting.
Hello, Dr. Shinde sir. Pardon.
Hello.
Sir, your
Yes.
voice is not clear. It's breaking. And one more thing is your presentation is not in presentation mode. So if it is in presentation mode, it will looks like better.
Okay. Okay. Now it's presentation. Is it in presentation mode? Is it okay now? Hello.
Hello, sir.
So is it in presentation mode?
It not, sir.
It's in presentation. Is it? It's in presentation mode. Hello.
Hello, sir. Not in presentation mode. I think your network is not stable. Voice is breaking and presentation is as it is. The slides are as it is and just moving. You just put it in presentation mode, so complete view will be there. F5. Yes, sir. Now it is okay. Hello.
I think I have an India so here, so that's why it's taking this issue. Your network is weak. Okay,
hello.
So
hello. Hello. Hello, Shinde sir. Please unmute yourself. Yeah.
Okay. Okay, so
your voice is not
I'm
coming.
talking about transparent collective. Okay, can you listen me now? My voice is clear.
Hello, Mahesh.
Yes.
This is Vivek. Nobody can listen you actually. So please check your internet connection. Maybe there is an issue.
My voice okay. Now okay.
No. Actually, we can't hear you. The sound is just breaking. The voice is not clear. And just check once
sir,
again.
your voice is not
let's
coming.
See.
Vivek, can you listen me now? Vivek?
Yes. Hello, Mahesh. I can listen.
Oh, I just came outside of my house. So
okay.
It is very slow here. So my main part of research is based on the transparent.
Dr. Shinde sir, your voice is not coming.
Yes, Vivek just say that my voice is coming. So, hello, Vivek.
Hello.
Yes, speak
Yes.
up.
Yes. I can hear you. Yeah, I can hear you clearly. Yeah,
Now
go
we
ahead.
are hearing you.
Okay, now I start my presentation again.
Yes.
Okay, my research is based totally based on transparent conductive electrode. So the transparent conductive electrode is a thin film which is optically transparent and electric conductive, made by the electric conducting material. So depending on its conductivity, there's many application of the transparent conductive electrode, such as OLED, solar cell, touch screen, and smart window. But basically, the material used for the transparent conductive electrode is indium tin oxide. But there's advantages for indium tin oxide is it's the lowest heat resistance and transmittance. For the many application, we need the highly conducting transparent conducting electrode with highly transparent. So indium oxide, we are getting these properties. But the disadvantage of indium tin oxide is like its cost is very high and is flexible, inflexible, and with brittleness. So many applications we need to replace the indium tin oxide from the transparent conducting electrode. So for my main research develop is on the replacement of indium tin oxide for the smart window. So for the due to the disadvantage of the indium tin oxide, we search many alternatives like this. So we study the different alternatives. The silver nanowire is the best material which can replace the indium tin oxide due to its application. It's like advantages such as electric conductivity, stretchability, its transparency, and thermal conductance. But still, the silver nanowire has its disadvantages. It has a non-uniform conductivity, high surface, and it's not stable in the ambient condition. But to solve this problem, we need to provide the passivation layer to the silver nanowire based the transparent conductive electrode. So there is many work is reported to protect the silver nanowire for the transparent conductive electrodes such as PEDOT-PSS, reduced graphene oxide, CNT, and metal oxide. But most of this passivation layer is only effective for short duration. So we need a proper passivation layer to protect the silver nanowire to use as in the TCE for the many application. So for that, my proposed passivation layer was like the different chemical, which is well-known corrosion inhibitor like 2-aminothiazole and benzotriazole. So this is well-known corrosion inhibitor, and it is provide the protection in different medium, such as the natural, acidic, alkaline, and oxidizing agent. So I use this corrosion inhibitor for the protection of silver nanowire. So for that, I just to check which corrosion inhibitor is good, we just coated the silver nanowire on the substrate with the corrosion inhibitor. And to check its corrosion, its stability, we put this electrode in the humidity chamber. The temperature for the humidity chamber is 85 degrees Celsius, and the humidity is 85 RH. So it's very harsh condition. And we put it like this for 6 days. And in 6 days, we find out that the benzotriazole is the best material which can protect the silver nanowire from the corrosion. So we find out that the benzotriazole is the best material, but we need to optimize to get the proper sheet resistance, like it's highly conductive and with the high transmittance. So for that, I made a different composition, such as I put 0.03 weight percentage, 0.07 and 0.1 weight percentage BTA, and I mix in the silver nanowire ink and I form the ink. So I just use a simple technique such as wire bar coating. For that, I just use ink. I just put it on the substrate and in coat wire bar. When as a wire bar is moved ahead, it's coat the silver nanowire on the PET substrate. We can in SEM we can see the randomly distributed silver nanowire, and after that I use like BTA TiO2 and corrosion inhibitor and coat on the fabricated electrode by spin coating, which is also simple method. So after coating, we can see that there's this welding of nanowire here, which is due to the BTA TiO2 solution, which makes heating due to chemical reaction, and there's a welding of nanowire, which is we can see here. So the sheet resistance for the silver nanowire PET is 48, but after the coating the right amount like 0.03 BTA, the sheet resistance we are getting, which is relatively similar to the 24, which is good enough for the application of the many devices. So we choose the BTA 0.03 weight percentage for our next experiment. So with this transparent conductive electrode, I put it in the humidity chamber again and I check its stability for the 30 days. So we can see that for silo nano PT, for 0 days, we can see the good nature of silo nanowire. But as days increases, 0 days, 20 days, 30 days, there's a oxidation of silo nanowire, and we can see this damage TCE. But only with the TiO2 CS, there is also the oxidation of silo nanowire after the 30 days. But with the BTA, we can see that after the 30 days, we can see uniform distributed silo nanowire, which is we can prove that the application BTA, which is a corrosion inhibitor, which provide the protection to the silo nanowire in the harsh environmental condition, such as 85 degrees Celsius and 85 RH. So this electrode is good enough to use in the commercial application, such as smart window, like solar cell and OLED. But my application is smart window. So further, I use this electrode in the fabrication of electronic device, which is a smart window. So this is our fabricated electrode, and I use the tungsten oxide ink, which is a best material for the smart window, which is change the color in the electrochromic reaction, which I coated through the spin coating, and after the drying in vacuum for 8 hours for the CT cells, I just put an electrolyte and another electrode we put in 2 electrode system. So, and this is fabricated our electrochromic device. So this is the TCE AG nanowire. This is the passivation layer. This is electrolyte. This is tungsten oxide, and this is the counter electrode. This is the structure of my fabricated electrochromic devices. So this is the workstation I use for the measurement, is how much is color and how much is the time taking to the coloration. So this is the result. So we can see that this is the transmitters 0 to 100 and this is the time. So when we apply the voltage, this we can see this transmitter is reduced to 80 to the 30, and when there's no voltage, there's again is the bleaching mode. But silver nanowire based ECD, which we know that is not stable, the first cycle is damaged because due to the voltage, there is electrochromic corrosion of silver nanowire and there's a damage of the ECD. But in case of the BTA and TiO2 CS based ECD, we can get like 50% coloration. So when we put this ECD, we can make indoor, we can reduce up to the 50% sunlight we can restrict from the coming to the home. So this is the basic principle. This is ECD. So why is tungsten used for the electronic device? Because when we apply the potential, the W, tungsten becomes this oxidation of the tungsten oxide, which makes it blue color. And when there's no voltage, this tungsten becomes again the yellow color. So you can see that this is the window in the normal condition. When we apply the voltage, it becomes the blue color. So here we can get like 80% sunlight, and in this case we are getting like 50%. We can restrict the 50% sunlight. So your like home is like cool mode because of the coloration of the window. And these windows at many airlines, they are using like blue color windows. So they're using the tungsten oxide for their application. So this is the like, flexible, like commercial now currently our windows are presently in the glass form, but my research is fabricating the flexible electrode. I think it's a future like for 20 or 15 or 20 years, all application will be the windows will be the flexible. So this is like the initial experiment to show the capabilities of the fabrication of the flexible electrochromic devices as such as a smart window. So after that, I studied the cyclic stability So as we know that silo nano is not stable in the electronic direction, the first cycle the device is damaged, and after that after the you can see that this is the TCE after the one cycle silo nanowire is completely like break silo nanowire is due to the oxidation of the silo nanowire. In case of TR2CS, TR2 added silo nanowire also, it's good for the first cycle, but after the 100th cycle, it's also silo nanowire is damaged. But in case of the BTA TR2CS, BTA added like corrosion added silo nanowire BT, it's worked like for the 1000 cycle, and you can see that the stable silo nanowire network even after the 1000 cycle. So I prove also to the XPS, I prove the role of BTA. So after the XPS also you can see that for the silo nano BT after first cycle, its XPS peak is shift to the left side, which is in the silver oxide region. And in case of the TiO2CS added engineer PT also, the XPS shift to the left side with silver oxide stage, which is show that there is oxidation and corrosion of the silver nanowire in absence of the benzotriazole is a corrosion enter. In case of the BTA like benzotriol added silver nanowire, even after the 1000 cycle, it's stable network and it's still in the silver net. So which proves that this benzotriazole which protect the silver nanowire in the electrochemical reaction, which makes the which allows us to use the silver nanowire to use in the smart window, which can replace in the future like indium tin oxide due to its disadvantages like its highly cost and its inflexibility and its brittleness. So this is like one of the device I make like big device like 6-fold increment. So for the first cycle, we can see that the device is changing its color. And I tested after the 1000 cycle, it's also still is working. So this is like initial experiments to show the capabilities of the silver nanowire based electrode for the flexible electrochromic devices. So this is the last slide. So I make slides very in hurry because I'm in vacation. So I conclude my presentation here, and if anyone has any question, I'm happy to answer.
Dear participants, the topic is open for discussion. If you have any queries or doubts, please free to ask. All the participants are requested. If you have any query or doubts regarding the session, please free to ask.
Kulal sir.
Yes, sir.
If there is no any question from audience, please conclude the session.
Okay. There are no any questions from the participants. Then I will conclude the session. Dr. Mahesh Shinde sir has explained very nicely on the topic, the transparent conductive electrodes, electrochromic devices. organic layer electrochromic devices. He has given very nicely in simple and lucid manner. On behalf of Vidnyan Mahavidyalaya Sangola, I thank you for Dr. Mahesh Shinde sir for given as a very nice lecture.
Okay, thank you to be
Over
having
to
here.
Shinde, sir.
Okay.
Okay, thank you, sir.
Okay, I will be
Thank you.
leaving the meeting now because I have to
Okay,
meeting
sir. Okay, sir.
next meeting. Thank you.
Okay, thank you, sir. Thank you, Dr. S.R. Kulal, sir, for valuable discussion and handling the session. Also, my sincere thanks goes to Dr. Mahesh Shinde, sir, for wonderful presentation on electrochromism. Thank you. Now we will start session 6, that is oral presentation. Session 6 is the oral presentation, and the session coordinator is Dr. B.B. Navle. So, Dr. B.B. Navle, sir, it's over to you.
Okay, thank you, sir. I'm audible?
Yes, sir, it's audible.
Okay, sir. Now, welcome everyone for today's session number 6, which is a poster presentation. Chairperson of this session is Dr. Kadam SM, who is from Department of the Chemistry, Vidnyan Mahavidyalaya Sangola. It's my great pleasure to introduce the chairperson, Professor Dr. S.N. Kadam, sir. Dr. S.N. Kadam is working as a assistant professor from last 13 years at Department of Chemistry, Vidnyan Mahavidyalaya Sangola. He has done his MSc in organic chemistry in 2008 with first class from Department of Chemistry, Yeshwant Mahavidyalaya, Nanded. Afterward, he completed his MSc. He completing his he is qualified NET exam, also SET exam in 2009. He also has been awarded by PhD degree in 2019 from Swami Ramanand Tirth Marathwada University, Nanded. The title of his PhD thesis is studies on the synthesis, characterization, and biological investigation of some novel heterocycles. He has got 3 patents has been granted for his research work. He also has been published 34 research papers in national and international journals, which are well-peer reviewed journals. With this brief introduction, I welcome and hand over this session to Dr. S.N. Kadam, sir. Now over to S.N. Kadam, sir.
Chief guest,
I am audible, sir?
Yes, sir.
Yes, sir.
Thank you, Dr. Navle, sir, for my brief introduction and handing over the session towards me. And now I would like to announce the names of authors of the today's selected presentations. Before that, I would like to give an instruction to the authors that the 5 minutes are allotted for 5 minutes are allotted for your presentation, and another 2 minutes are there for the discussion. Okay, and be ready with your PowerPoint presentations. Okay, so now I would like to announce the names of the authors of today's selected presentation. Mr. Bhalachandra Krishna Mandlekar, Derle Sonali Ashok, Mishra Shraddha Rajnarayan, Pritiyam Patil, and Ankush Prakash Pawar. Be ready with their PowerPoint presentations. Now, I would like to call the first author of today's oral presentation, that is Mr. Bhalchandra Kashinath Mandlekar from Institute of Science, Mumbai, on tungsten oxide hill flame synthesized by electrodeposition for electrochromic applications. Okay, over to Bhalchandra Kashinath Mandlekar.
Good morning, sir. Am I audible to you?
Yes, yes. You are audible.
Sir, I'm sharing my PPT. Is it just a moment? Is it visible?
You are not visible, sir.
Okay. Just a moment, sir. Is it visible now?
Yes, sir. Your presentation is visible now.
Good morning to all, sir. Just a moment, sir. This is slide show is not happening. Sir, I'm over here presenting tungsten oxide in synthesized electrodeposition for electrochromic application. Just now, Dr. Shinde had a brief over electrochromic application. So this is me, Mandekar, and Jadhav, Umar Jadhav, Sharaj Jadhav, and our guide, Dr. Nano-Materials madam. The tungsten trioxide thin films were developed, having developed on FTO, that is fluorine oxide, which is a transparent conducting oxide. Over here, 0.3 molar W3 nanomaterial we have developed. And color efficiency, what we have observed is 192.20 microcoulomb at 630 nanometer. This this electron deposition of W3 is giving us a high efficient electrochromic application. Some materials exhibit reversible change in color under influence of light, heat. These phenomena are respectively called as photochromism and thermochromism. Some materials show reversible change in color due to influence of electric field, and this is what electrochromism is. Electrochromism is mainly shown by two categories of material. One is inorganic, another is organic material. In inorganic material, there are mainly transition elements, and one of the very important transition elements is tungsten. Tungsten shows remarkable change in coloration and decoloration. Tungsten oxide is most reviewed and electrochromic material due to its electrochromic properties. Just now, Dr. Shinde has also mentioned WO3, how it changes its color. So my job is halfway done. In this article, we have deposited WO3 an FTO glass by electrodeposition material. This how we have synthesized. We have taken AR grade of tungsten acid powder. We dissolve in distilled water and we get the magnetic stirrer for RPM of 400 for 15 minutes. While stirring, the ammonia was added clockwise to change the pH to 12. After 15 minutes of stirring, the solution was filtered with a filter paper and we got a clear solution. Meanwhile, FTO glasses of size 1 into 3 centimeters was washed and cleaned with acetone. The FTO glasses further cleaned by keeping in solid for 15 minutes. By QLIC process came. The FTO glass was inside a thin electrode. The precursor solution was and platinum use was found to be electrode. Electrodeposition time was set for 900 What we found result, the X-ray diffraction. The X-ray diffraction revealed that the different W3 nanomaterials are similar in nature. The observed W3 peaks were well matched with this 072 at 2 theta values of 17.46, 26.43, 31.21, and Miller indices we observed 020, 11, and so on. The observed peaks of FQ also show the peaks at 33.8, 37.6, and so on. So this graph shows the rest part of this particular graph shows amorphous nature. and therefore we say that it is semi-crystalline on FPO substrate. We have also done FPR analysis. In FPR analysis, we got the graph that pure WO3 samples have sharp and intensity of peaks near at 593, assigned to WO tungsten oxygen and tungsten bridging variation long at corner sharing of octahedron in WO3 crystal. The broadband in 270 370 division indicate 944 indicates that hydroxide OH group is present in the sample. The sharp peak observed around 1409 indicates the presence of ammonia complex, since we have added ammonia, yes, and water molecules in the liquid. In addition to peaks, Peg41 was also observed, corresponding to vibration form. Then we have done the cell analysis. In cell analysis, we found this crack morphology. The WO3 deposited on F2 depicts the crack morphology, structure, the size of 100 to 200 nanometer, including the existence of dense interconnected granule morphological structures. The observed cracks are more suitable for discussion of electrolyte and intercalation in the intercalation process, which is investigated in further electrochemical studies. Then in electrochemical studies, cyclic voltammetry of WO3, where we found large area. It shows that CV of WO3 analyzed using scan rate of 100 milliwatts per second in 0.5 lithium percolate and TC electrolyte. Demonstrate that current density of WO3 deposited on F2 is large current density, which promotes higher diffusion. WO3 nanomaterials plus 0.5 15 volt anode bleaching starts while cathodic coloration starts at minus 0.36 volt, which shows slight possibility behavior of nanomaterials. Strong reversibility of the WO3 deposited on SPO indicates that the flame continue to operate as effective intercalation and intercalation cause and indicate remarkable endurance. Now, coloration and decoloration we have taken, the transparent exposes the wavelength we have taken, and the black one is decoloration state and the red one is coloration state. Over here, the redox couple is shown below in the coloration and decoloration states. WO3, this reaction, what is expected, WO3 is more lithium, giving the electron, and lithium and WO3 bonds form, which is blue in color. And then it is again reversible reaction. We get as when the electrical is not there, we get the WO3 back. So optical density over here we have calculated by the formula now of dB by dC raised to 10, and optical density what we found is 0.3444, which is nearby what Dr. Shinde just told about. We got around 20 to 14. So I think it is one and the same. Then we have found the response time of this and response time for coloration and decoloration, which is lithium percolate, is found to be very fast. It is 1.29 seconds for coloration and 1.22 seconds for decoloration. This graph shows. And what confusion I'll get is that one step WO3 nanometers were successfully deposited on FPO by using this detection. The analysis of XRD in FPR confirmed that WO3 can be successfully deposited on various substrates. The same analysis shows WO3 is a crack morphology. The CV analysis revealed that as deposited WO3 is highly reversible at potential 0.9 volt to 1.1 volt. The observed maximum coloration frequency of FPO is 193.2 centimeter square at 633 nanometer wavelength. The fastest electron coloration with response time of nanostructure WP is 1.29 and 4.22 seconds. Thus prepared one-step binder 3 WP nanostructure material on FPU is highly efficient for the applications. These are my references. And I acknowledge over here Dr. Ekter, my guide and supervisor, my colleague Thomas Yadav. Thank you. Thanks.
Thank you for your presentation, Mr. Bhalchandra sir. So now session oral presentation is now open for the queries and questions. Anyone there to ask the questions can ask.
बरं चालतंय ठीक आहे.
Session is open for the discussion. Is there any questions? Okay. Now, since there is no any question for Mr. Bhalchandra, I would like to call over the next participant of the oral presentation, that is Derle Sonali Ashok. She from Karmavir Shantaram Bapu Pondaji Bhavre Arts, Science and Commerce College, Uttam Nagar, Sitco, Nashik. So I will welcome the participant, and now you are set to start your presentation. I would like to inform all the participants to mute their audio, and again I would like to inform the authors of the oral presentation that they should ready with their PowerPoint presentation. Okay. Madam.
Okay, sir. Oh, thank you, sir. Audible, everyone?
Yes, madam. You are audible.
Yes, sir. Good morning, everyone. Today, oral presentation topic on biosynthesis and characterization of zinc oxide, copper oxide nanocomposite mediated by Agar marmoleous leaf extract. My research work abstract is green synthesis play a very important role in our method. Synthesis of zinc oxide and copper oxide nanocomposite by leaves extract. The synthesis nanocomposite are characterized using three techniques: XRD, UV, and FTIR. We calculate in XRD crystalline size, then UV range between the formation of nanocomposite, then FTIR technique we found the peak in a functional group where which functional group are present in this composite. Nanotechnology is based on my research work. Nanotechnology is a science, engineering, a system, molecules having one more dimension on order of 100 nanometer million. Then nanoscience is also based on our research work. Nanoscience many widely application in computer biology, material science, chemistry, physics, biology, and etc. Nanoscience is the phenomena occurring in system with nanometer dimensions. Then introduction by metal oxide semiconductor have widely used for photocatalytic environment. It has been demonstrated that coupling of different nanostructured semiconductor to form nanocomposite. Why we get nanocomposite? Because the mechanism of nanocomposite by mutual transfer of charge carriers from one semiconductor to another with compatible chemical and electrical properties. Most of the optical properties in nanocomposite are important. Then zinc oxide, copper oxide, our material, metal oxide is potential material because high thermal stability, low cost. Properties of zinc oxide, copper oxide are size dependent, where particle size is reduced to the nanometer. This is the crystal structure of zinc oxide and copper oxide. Then properties of zinc oxide, copper oxide, nanocomposite. Many properties are involved in molar mass, order, density, melting point, and etc. Then synthesis method of nanomaterials. Synthesis, widely synthesis method of nanomaterials. There are two basic methods: top-down approach and bottom-up approach. In top-down approach, physical method are involved, and in bottom-up approach, chemical method and biological method are involved. Technique to synthesize the nanomaterial. Nanotechnology is interdisciplinary subject. There are therefore various methods in synthesis of nanomaterial, but we get the biological method to synthesize the material. Then green synthesis method of nanomaterial. Green synthesis method to understand the properties of material in toxicity studies and to design nanoscale material for high performance products with little. Then several chemical methods are available for synthesis of nanoparticles, copious react and starting materials in reactions, toxic, potential hazardous, environmental, etc. These are the green biological method. Then advantages: green synthesis method widely advantages, eco-friendly approach, non-toxic in nature. Then in large-scale production, then external experimental condition like also biological component itself act as reducing and capping agent. These are widely application. And then this is a synthesis of nanoparticle by plant extract. First of all, we take a plant part, then boil it, washed with distilled water, squeeze it and filter. Then after that, respective salt solution. Also solution color changes. Then separate nanoparticle. We get the particle. Then plant introduction. Aglomargolose, my plant introduction to family Rutaceae. The popular name is Shiva and Vishnu can be grown in every house. Flowering occur in April, May soon also. Then this is plant profile scientific classification. Also scientific classification by plant. Some phytochemicals are found in my plant chemicals are chemical compounds produced by plants. Generally, these are the phytochemicals contain numerical phytochemicals. Then schematic of zinc oxide, copper oxide nanoparticles using extract. These are the application of various activity in a aglomargolose leaf extract. Then medicinal use are also important in a synthesis method. These are widely medicinal use in a medicine for loss appetite. Then also widely application in this plant extract. Then characterization technique are most important in a synthesis method. There is three characterization. First is the X-ray diffraction. Second is the Fourier transform infrared spectroscopy, and third one is the UV spectroscopy. Then first detail is X-ray diffraction. X-ray diffraction method is based on the constructed interference of monochromatic X-ray and crystalline sample. Why we get XRD? Because it measures the distance between two layers. It also determines orientation of single crystal or grain structure. We analyze the structural analysis of XRD. We get the crystalline size. A crystalline size of zinc oxide, copper oxide nanoparticle is 14.8 nanometer. Then we get calculation of a peaks, plane peaks, HKL plane. We get the crystalline size of particle is the 14.8 nanometer average particle size. Then various interplanar spacing for all peaks of zinc oxide, copper oxide are calculated given table. We get the 2 theta in HKL plane, then full width half maxima, this spacing, grain size and HKL plane after calculation. Then second characterization technique is FTIR. FTIR principle based on when IR radiation pass through the sample, some of the radiation is absorbed. It also identify the characterized unknown material, identify the contamination or in material. This is schematic of FTIR. Then we analysis of FTIR graph. We calculate the functional group in present in the extract, and functional group plant material is of zinc oxide, copper oxide nanoparticles. Table FTIR analysis, wave number found in their group, which bond group are present and which functional group are present in their wave number. Then third technique is UV spectroscopy. UV spectroscopy is based on the Baird-Lambert law, which states that the concentration of sample and path length is directly proportional to the absorbance of light. This is schematic of UV spectroscopy. Then this is analysis of UV graph. First graph is the zinc oxide, copper oxide nanocomposite, and second is the tau plot. First graph is in energy band graph in electron volt, and Second graph is tau plot. We calculate the energy band gap for indirect transition and direct transition. This is composite. Why we get composite in our synthesis method? Because composite method, this is for example of zinc oxide and copper oxide. Before nanocomposite formation and after nanocomposite formation, mutual transfer charge carriers between one semiconductor to another semiconductor. This is application in copper oxide and zinc oxide, semiconductor, optical application, electrical, magnetical properties, and also various applications such as development of supercapacitors, near IR filters, then magnetic storage media, sensors, catalysis, and semiconductors. This is also application methods in synthesis application of both nanocomposites. Conclude, simple and inexpensive method was established for the green and eco-friendly synthesis of biometallic composite, hygromargolose extract, reducing and stabilizing agent. We calculate the three techniques of X-ray, EFT, IR, and UV. In EFT, IR, we calculate range between the spectroscopy 327 to 356 nanometer, which confirm the formation of nanocomposite. EFT-IR technique, we calculate the functional group detected peak where present in extract. Then UV, we calculate the absorption range between an XRD crystalline size is found between 14.8 nanometer. Some references are used in this technique.
All the authors are instructed once again for completing their presentation within time. Okay.
I would like to thank for head department, our college, and also teacher to guide me, and also friend.
Okay.
Thank you, everyone.
One question is there.
Okay, sir.
Now used the agar marmolis leaf extract. You have checked the pH of that extract. What is it?
Yes.
Is it acidic or basic?
Yes, sir. Check pH.
Did you have checked the pH of that extract?
Yes, sir.
Or basic?
Acidic.
Acidic pH. Okay, thank you, madam. Is there any question from participants? Is there any question? I request to mute the audio of the participants. So, okay, thank you, madam. Now, I would like to call the another participant, that is Mishra Shraddha Rajnarayan from Karmavir Shantaram Bapu Undaji Wavre Arts, Science and Commerce College, Uttamnagar, Sidco, Nashik, on the topic biosynthesis and characterization of Mn3O4 nanoparticles mediated by Maduka longifolia plant leaf extract. Okay, over to Mishra Shraddha Rajnarayan.
Am I audible?
Yes, ma'am, you are audible.
So good afternoon, everyone. I am Shraddha Rajnarayan Mishra from KSKW College, Sidco, Nashik. So my research work done in biosynthesis and characterization of Mn3O4 nanoparticle mediated by Maduka longifolia plant leaf extract. So abstract. So metal oxide nanoparticle has been studied worldwide by research. The green synthesis of nanoparticle are eco-friendly. That's why I choose green synthesis. So here I have done three characterization techniques: XRD, FTIR, and UV visible. So introduction of nanotechnology. It is a study of an extremely small thing having range 1 to 100 nanometers. These are the application of nanotechnology. Nanoscience and application of nanoscience. So metal oxide, a chemical compound formed by metal and oxygen, is known as a metal oxide. So why I prepare Mn3O4 nanoparticle? It is most stable oxide in manganese series. It is applied in numerous industries like magnetic and electrochemical industries. That's why I prepare Mn3O4 nanoparticles. The property of Mn3O4 nanoparticles. Here are application of Mn3O4 nanoparticles, energy stores, absorption material in and drug delivery or etc. It's having basically two synthesis, top-down approach and bottom approach. So I use green synthesis. It is type of bottom approach. In green synthesis, I use plant leaves for extraction. So green synthesis, why use green synthesis method? Because it is inexpensive, not harmful for anyone, and non-toxic. That's why I choose green synthesis method. So here are advantages of green synthesis: non-toxic, cost-effective, eco-friendly, and etc. So I use Maduka longifloria for synthesis. It is belong to palms family, and it is generally found in Uttar Pradesh, West Bengal, Bihar, and other states. These are phytochemicals present in the Maduka longifloria: starch, minerals, protein, phenolic acid, vitamins, cardiac oxide, and titanium. Here are medical uses of longifloria. This is a symmetric diagram of Mn3O4 nanoparticles. So here are the list of characterization technique, but I have done mainly three characterization techniques: XRD, FTIR, UV visible. X-ray diffraction based on the Bragg's law, constructing interference of nanostructure. X-ray are a crystalline range. By X-ray, we can found crystalline size, d-spacing of a crystal structure, and lattice parameter. These are the XRD analysis and our graph of Mn3O4 nanoparticle. The average crystalline size are calculated by Debye-Scherrer formula is found to be 12.4 nanometer. The d-spacing Mn3O4 nanoparticle calculated by Bragg's formula is found to be 3.82 angstrom. The lattice parameter of Mn3O4 nanoparticle calculated by XRD data is 16 angstrom. So these are the calculation of XRD. The average particle size we are found 12.4 nanometer. This table is a value of interplanar spacing of all peaks for Mn3O4 nanoparticle calculated by given table. Here are peak numbers: 2 theta degree, full width, half maximum, d-spacing, green size, and HKL plane. Here are FTR. When infrared radiation passes through a sample, some of the radiation is absorbed. The radiation that passes through the sample is recorded. By FTIR, we can determine the functional group of our molecule and the fingerprint region. These are the analysis of FTIR.
Ishra ma'am, please try to conclude.
Hello.
Yes, ma'am. There is a time limit. Please try to conclude it earlier.
Okay, sir. Okay, sir. This is graph of UV analysis. So I have successfully synthesized Mn3O4 nanoparticle by using Maduka leaves. By using XRD, FTIR, UV visible characterization, we can calculate average d-spacing is found to be 3.82 angstrom. Lattice parameter is 16 angstrom. Optical band gap is 3.6 electronic volt. Acknowledgement. So here I would like to thank our HOD, Dr. A.B. Gawande sir, our principal S.K. Kushare sir, our technical and non-teaching staff. Thank you all of you for your valuable guidance.
Now the presentation is open for the discussion questionnaires. If anyone wants to ask the question, they can ask.
Yes, sir. Hello.
Yes, you are audible.
Yes, sir. I have one question. What does the procedure for synthesis of Mn3O4 nanoparticles?
Sir, green synthesis.
What you have done in that particular synthesis procedure? Shortly,
yes.
Shortly explain.
Sir, basically, I have characterized XRD, FTIN, and UV analysis by
No,
XRD
madam, no.
crystalline size.
My question is what does the procedure for synthesis of these nanoparticles? How you synthesize these nanoparticles?
That is, ma'am, which process, which method you can use?
Adapted. Yes.
Okay. So, sir, I am bottom-up approach, sir, I use for this synthesis.
Okay. Have you got it?
Okay, sir.
Okay. Okay. Thank you. Now I would like to request next oral presentation participant, that is Preeti M. Patil from Gulbarga University, Karnataka, and he is delivering the oral presentation on applications of doped ZNO nanocomposites. So, okay, it is over to Preeti, madam.
Yes, sir.
Audible, you can.
Am I audible, sir?
You are audible. You can start your presentation.
Yes, sir. Just I'll share my slides, sir. Just a minute.
Before that, I would like to say that there is a time limit of 10 minutes, 5 minutes, and 2 minutes for the questionnaires. You have to conclude in the time.
Yes, sir. Hello.
Now your time starts now. Okay.
Yes, sir. Am I audible, sir?
Yes, you are audible.
Yes, sir. Sir, good afternoon, everyone. First of all, I would like to thank the organizers of International E-Conference on Recent Trends in Nanomaterials and Its Applications 2023 for giving me an opportunity to present my paper here. Myself, I am Preeti Patil, and I am a research scholar working in Gulbarga University, Karnataka, sir. Today, I am going to present a paper on applications of doped zinc oxide nanocomposites. So to start with, I would like to give some introductory note on zinc oxide nanocrystals. Zinc oxide is an N-type semiconductor having a wide band gap of nearly 3.37 electron volt at a room temperature and a high exciton binding energy of nearly 60 MeV and a hexagonal Woodside structure with lattice constant A/B equal to 0.325 nanometer and C equal to 0.521 nanometer. Zinc oxide nanocrystals, they have been a hot academic topic because of its unique characteristics like low cost, non-toxicity, abundance in nature, biocompatibility, and also it exhibits some novel optical, electrical, chemical, and mechanical properties compared to their bulk forms. So due to their unique properties, they have numerous applications in the fields such as sensing, light emitting diodes, photocatalysts, solar cell. But however, its wide band gap has limited practical use of ZNO nanoparticles as photocatalyst or as an antimicrobial agent. Photocatalytic efficiency is relative to the surface chemical reaction and electron-hole recombination. If the electron-hole recombination is too fast, then the surface chemical reaction will not occur. The photocatalytic efficiency will be low. So the method to restrain electron-hole recombination is the key to increase the photocatalytic efficiency. So in order to improve the optical, electrical, magnetic properties as well as the photocatalytic properties, different or distinct elements are doped in ZNO. Doping represents a valuable approach to tune various ZNO properties by altering the ratio of doping elements and controlling the methods and conditions of synthesis. Present study is focused on diverse technological and medicinal applications of doped ZNO nanocomposites. In this slide, we can see the synthesis technique used for the doped ZNO nanocomposites. So synthesis technique used are broadly classified as physical, chemical, and biogenic methods. Chemical synthesis techniques are found to be cheaper, faster, and they produce pure desired crystals with high stability and high yield, and than the other synthesis techniques like physical and biogenic. So some of the synthesis methods and their merits are listed in the table, such as Sol-Gel method is listed, hydrothermal method, co-precipitation method, solid state reaction, combustion synthesis, microemulsion methods, and many more. In the synthesis of doped zinc oxide nanoparticles, actually we use the precursors, zinc precursors like zinc acetate, zinc nitrate, or zinc chloride salts, which are used for the doping in case of doped zinc oxide nanoparticles. Regarding applications of doped ZNO nanocomposites, there are various applications of zinc oxide nanocomposites, like they are used in photocatalytic degradation, gas sensing, solar cell application, photoluminescence, photodetectors, antimicrobial activities, antibacterial activity, antifungal activity, and cosmetic and pharmaceutical industries. These applications are achieved or improved by doping the distinct elements into ZNO by various techniques. And the techniques I have already discussed, the various synthesis techniques you can use. For photocatalytic degradation, actually photocatalysis is an important electrochemical process which occurs under light irradiation either from the sun or artificial light source at the surface of the photocatalyst. When energy of incident photon is greater than or equal to the energy band gap of ZNO, then what happens is the reactive species are produced, which are strong and oxidizing agents that facilitate the photocatalytic process of degrading the organic and pharmaceutical pollutants. Actually, if you are studying, if you go through the various papers, because this is the research paper, so I have referred many of the research papers. I have seen that by non-metal doping like carbon and nitrogen, they also enhance the photocatalytic activity. So carbon doping, 30% carbon doping samples show thrice the absorption compared to the undoped ZNO. Similarly, nitrogen doping effectively reduces the band gap from 3.06 electron volt to 2.87 electron volt, and it is found beneficial in increasing the photocatalytic activity by almost 8-fold. Doping of transition elements narrows the band gap of ZNO and improves the absorption of visible light, of solar spectrum, and CE doped ZNO, AG doped ZNO are also found to enhance the photocatalytic activity of ZNO. If you go to the gas sensing application, so gas sensing property of the doped ZNO depends on the surface parameters like area, porosity, defect present in the surface. Yes, sir. Concentration and working temperature. Aluminium doped ZNO thin films show high response and recovery towards ethanol gas sensing. Similarly, iron, nickel, cobalt, copper, gold, and silver also shows the different gas sensing activities. If you come to the antimicrobial or antibacterial activity, the reactive species produced by photocatalytic degradation can be used as antibacterial agent that can rupture the outer membrane of the bacteria, inhibiting the growth. Doped ZNO is categorized as most promising inorganic antibacterial agent that are more stable and safe and can be used in the absence of ultraviolet light. Similarly, Ag, Cu, Ni, Mg, Fe can also enhance the antimicrobial activity. Zinc oxide with nickel exhibit higher optical activity and also possess potential antibacterial qualities. As compared to gram-negative bacteria, their activity is found to be more promising. Ag doped ZNO is effective in treating contaminated water released from industries, including textile, dye, pharma, paper, etc. Ag doped ZNO is used as antibacterial reagent. Solar cell applications, if you just see nickel as well as tin, they are very successful in enhancing the power efficiency of the solar cells. In case of tin, it is found that 0.05% doped tin, it almost produces the efficiency of 17.81%. In case of medicine and pharma, you can see zinc, copper doped zinc oxide, which is synthesized by green synthesis. It is used anti-cancerous properties, show anti-cancerous properties. They are used in sunscreen, they are used in antibacterial as well as antioxidant effects. Mg doped ZNO has proven to be inducing the cell death in human breast cell cancers. Gadolinium and European show phototoxic behavior against normal and tumoral cells. So these are some of the applications of doped zinc oxides. So if I would like to conclude this,
please conclude. Conclude, madam.
Yes, sir.
Please go to
Yes, sir.
conclusion of your.
So doping changes the properties of ZNO nanoparticles and it improves suitability for the use in variety of applications, including gas sensing, photocatalysis, and antimicrobial activity. The study has taken into account a lot of pertinent research on application of doped zinc oxide nanocomposites. The use of multi-doped antimicrobial agent that combines metal and non-metal composites could represent a crucial advance in eliminating high-resistant microorganisms. So still we have a scope of developing multi-doped which can be a best antimicrobial agent and which can be full in eliminating highly resistant microorganisms. So with this, I would like to acknowledge my guide, Dr. Basavaraj Sanaki from Department of Physics, Gulbarga University, Kalburgi, and Dr. Sridhar Mathad, who has guided not in this work. He is from Kerala Institute of Technology, Hubballi, Karnataka. So these are the references which I have done for this work. Thanks.
Okay, thank you, madam. Now I would like to call the next participant. Okay, before that, any questions from the audience? Any question from the audience? Okay, if there are no questions, then I would like to call the next participant of oral presentation, that is Ankush Prakash from Mandal College of Pharmacy, Solapur, to start his oral presentation, practical method development and or RPHPLC method. Metacarpamol in bulk and formulation. Okay, Ankush, it is over to you. Now you can start.
Yes, sir.
Okay, Ankush,
Yes,
you are audible. Start your presentation and complete it within time. There is a time limit of 5 minutes. Okay.
Good afternoon.
Okay.
Sir, I am audible, sir?
Yes, you are audible. Just start your presentation.
Okay. Good afternoon, everyone. Analytical method development and validation of RHPLC method for the estimations of methocarbon in bulk and formulation.
Hello.
Hello, sir. I am audible.
Yes, you are audible. Just start your presentation.
Yes, sir.
You have to complete it within time. 5 minutes are given for your presentation.
Okay.
Your screen is also visible.
Screen is not shared.
Screen is also visible. Now it has gone.
Visible, sir? Screen?
Yes, it is visible. Just start your presentation.
Not working in.
Hello.
Hello, sir.
Your audible and presentation is also visible.
The screen is not visible, sir.
Before it was visible. And now it is visible. Is it visible to you?
Yes, sir.
Okay.
Screen.
It is visible to us now. Is there any technical problem? You should scroll from here.
Kadam sir, please conclude the session.
Okay. There is some technical problem with the presentation. So we will conclude here the session. So I am very gladful for listening the oral presentations of all the participants. I am very thankful for the organizing committee for giving me opportunity for chairing a session. So okay, thank you. I am handing over the session to the Thombre sir.
Hello, sir.
Dr. Navdi sir.
Okay, we are very thankful to Dr. Akkadam SM for chairing this session. Also, I am very thankful to all researchers who present their research work now. Finally, I am thankful to all participants. Now, over to a convener of this conference, Dr. Thombre sir. Over to Thombre sir.
Okay, thank you, sir. Thank you, Kadam sir. And thank you, Navle sir, for chairing the session. The last session is the valedictory function, and the session coordinator is Mr. A.M. Kamble sir. So, it's over to you, Kamble sir.
Okay, I'm audible? Yes.
Yes, sure.
Yes. Okay, thank you. Now we are in the last session of this e-conference, that is session 7, valedictory function. The first, the time has come to draw a curtain of our program. A very good afternoon and warm welcome to all of you to this valedictory function of this international e-conference on recent trends in nanomaterials and its applications 2023. As we start with the valedictory function, I now take this opportunity to welcome our honorable chief guest, Professor Dr. R.S. Mane from Swami Ramanand Tirth Marathwada University, Nanded, and the president of this function, Dr. Ashok Rao Shinde, Director, Sangola Taluka Shetkari Shikshan Prasarak Mandal, Sangola, and our college principal, Dr. S.M. Mulani, the head Department of Physics, Dr. B.B. Navle, IQAC coordinator, Dr. S.S. Dasade, and convener of this conference, Dr. J.V. Thombre, and also it's my colleague, Dr. Bandgar and Dr. Siddhudan Kadam. Our esteemed dignitaries and participants of this conference present through online mode. Participants were very enthusiastic. I am thankful to all the participants for attending the e-conference. I am sure that the participants must have benefited by attending this conference. Now I would like to request Dr. J.V. Thombre to overview to share the overview of this e-conference.
The president of valedictory session, beloved director of Sangola Taluka Shetkari Shikshan Prasarak Mandal, Honorable Dr. Ashok Shinde sir, chief guest of valedictory session, senior professor and well-known scientist in electrochemistry across the globe, Professor R.S. Mane sir, guests from abroad and participants in the conference, my dear friends, ladies and gentlemen, I am here to present the report of International E-Conference on recent trends in nanomaterials and its applications 2023, that is RTNA 2023, held in the Department of Physics of Vidnyan, Mahavidyalaya, Sangola. I reiterate my gratitude to Honorable Principal Dr. Sikandar Mulani sir for planning this conference as a recurring event of department, and thanks to my colleagues in the Department of Physics for entrusting the responsibility of organizing the conference to me. This conference was attended by in all 150 research scientists from across the globe, including Sydney, South Korea, and US. The research scholars numbered 120. In all, we had 4 invited talks spread over 4 sessions in the past 2 days and examined 12 oral presentations. These oral presentations were judged by 2 experts, Dr. S.M. Mane from South Korea and Dr. S.N. Kadam from Vidnyan Mahavidyalaya Sangola. Both of them agreed that they were of very high standards and it was indeed a difficult task to judge them in the stipulated time. Considering the huge response that was generated, we had to conduct the invited talks of speakers and oral presentations of participants via Zoom, meeting digital platform and YouTube live streaming. Surely there must have been some lacuna and I apologize for inconvenience caused. My colleagues in the Department of Physics are valuable assets of the department. Not only they work hard in their own research work, but they also pour their hearts and work relentlessly for such activities as this conference, right from planning to the execution stage. I have to express my special thanks to them. Our alumnus, Dr. Sagar Mane and Dr. Vivek More from South Korea, have taken more efforts to make this conference successful. So my sincere thanks goes to Dr. Mane and Dr. More also. The conference is coming to an end and with a heavy heart I bid farewell to you. We will keep meeting through the pages of the journals and also through many more such conferences, some of them again in Vidnyan Mahavidyalaya Sangola. Goodbye and thank you. Thank you.
Thank you, sir. Now we are moving towards the feedback from the participants. First, I will call Gaikwad Swati from Karmavir Shantaram Bapu College, Sidco, Nasik.
Okay.
Please.
Good afternoon, all of you. I am Swati Gaikwad, MSc Physics Part 2 student from KSKW College, Sidco, Nasik. First of all, I would like to say thank you, Dr. Jagannath Thombre sir, for giving me an opportunity to explore my ongoing research work. I would also like to thank you, Sangola, Taluka, Shikshan, Prasarak, Mandal, Sangha, Vidnyan Mahavidyalaya, Sangola, for conducting this e-conference and giving us opportunity to present our paper. I got to learn the recent trend and ongoing research work on nanomaterials and its applications. I would also like to thank our principal, Dr. Pushare sir, and our head of department, Dr. A.B. Gawande sir, for encouraging us to take a part in this e-conference, international e-conference. And it was a very nice experience. I enjoying this international e-conference. Very nice. Thank you. Thank you, all of you.
Thank you. Next, from the students, that is Sheikh Sabanaz from Sidco College, Nasik. Sheikh Sabanaz from Sidco College, Nasik.
Good afternoon, everyone. I am Sabanaz Sheikh, a student of MSc Physics Part 2 from KSKW College, Sidco, Nasik. First of all, I want to thank Dr. Jagannath Thombre sir for conducting this conference and the Sangola College. Not only this conference gave me a lot of knowledge, but also we get a field of expertise of this conference. I would also like to thank the principal, Sir Dr. Pushare, and HOD Department of Physics, I.B. Gawande sir. Thank you. Thank you so much.
Thank you. The last feedback from the delegates, Professor Ketan Gaikwad, Somaiya College, Mumbai.
Hello, am I audible?
Yes, yes.
Okay. So first of all, I would like to congratulate principal of Vidnyan Mahavidyalaya Sangola and organizing committee of International E-Conference on Recent Trends in Nanomaterials and Its Applications 2023. That is RTNA 2023. All the invited talks, right from Professor V.B. Patil sir, and till today's last but not of course least, Dr. Mahesh Shinde, each invited talk was fruitful in the sense that these talks have delivered knowledge about nanofabrication technique, sensor technology, organic photovoltaic, and solar photovoltaic, of course, and most importantly, green hydrogen production. So all these talks were definitely fruitful for all of us, all participants. Also, oral presentations by students was fruitful. These oral presentations were consisting of applications of nanoscience and nanotechnology. So in all, the purpose of the e-conference has been met. So once again, I would like to congratulate all organizing committee members and principal of Vidnyan Mahavidyalaya Sangola. Thank you.
Okay, thank you, sir. We are too much eager about to hear the chief guest of this conference, valedictory function. So I would like to request Dr. S.S. Dasade to introduce the chief guest of this valedictory function.
Okay, thank you, sir. Very, very good afternoon to all of you, my friends. Sangola Taluka Shetkari Shikshan Prasarak Mandal Sangolas, Vidnyan Mahavidyalaya Sangola, Department of Physics, in collaboration with Internal Quality Assurance Cell, organizes an international e-conference on recent trends in nanomaterials and its application 2023. It is my great pleasure to walk you through the conference, introduce you to the speakers and delegates that have come from all over the country and also from the country, also from other country, to share their knowledge and enhance our mental horizon. Today's speaker of valedictory session and guest of honor, esteemed Professor Dr. R.S. Mane Sarji, Swami Ramanand Tirth Marathwada University, Nanded, Chairperson of the valedictory session, Honorable Dr. Ashokji Shinde, Director Sangola Taluka, Shetkari Shikshan Prasarak Mandal, Honorable Principal of the College, Dr. Sikandarji Molani, Dr. Navle Bibi, Head of the Department, Dr. J.V. Thomre, Convener of the Conference, the Ashok Kamble, Dada Mandgar, foreign invitees and participants of the conference, my dear friends, ladies and gentlemen. I am immensely happy to welcome you all in the last session of e-conference and to Vidnyan Mahavidyalaya to the International Conference on Recent Trends in Nanomaterials and Its Application. And it is my great pleasure to introduce esteemed Professor Dr. R.S. Mane sir. He received his PhD in physics from Shivaji University, Kolhapur, and worked as a postdoctoral fellow at Angnom University, South Korea. He also was on research faculty of Oxford University, United Kingdom, since 2010. He has been a senior professor and director at SRTM University, Nanded, and visiting professor of Pasun National University, Korea. He is with more than 400 research articles, nearly 13,000 citations, and I-10 index of 240. He is actively engaged in studies in synthesis of 2D and 3D metal oxides, chalcogenides, carbides, nitrides, and fluorides for the preparation of solar cells, and also for the preparation of electrochemical supercapacitors, and in case of chemical sensors and bioactive applications. His major interests include synthesis of novel nanostructure for energy generation, conversion and storage device technologies, in addition to understanding their theoretical behaviors. He is one of the 2% global research scientists declared by Stanford University, USA for the year 2020-23. He was visiting professor in year 2013 to 17 in King Saud University, Saudi Arabia. He is visiting professor in year 2017-18 for Pasun National University, Korea. He is also visiting professor in Sri Guru Gobind Singh Institute of Engineering and Technology, Nanded, which is situated in India. Brainful Fellowship he got in year 2006 to 7 in Anang University, Seoul, South Korea. He is a member of academic and research bodies. He is Associate Editor, Discover Materials. He is BOS member of North Maharashtra University, Jalgaon, member of Secretary of Board of Deans and Director, SRTM University, Nanded. He becomes as a member Secretary Board of Research, SRTM University, Nanded, member Secretary Board of Innovation, Incubation and Enterprises, SRTM University, Nanded. He becomes as a member of Secretary Board of National and International Linkages, SRTM University, Nanded. He is editor of many reputed journals, research and reviews in electrochemistry, functional nanomaterials. He is also a member of Academic Council and Senate, SRTM University, Nanded. Honorable Professor Dr. R.S. Manesarji is a member of Senate, SRTM University, Nanded. He is again BOS member of Rajeshri Shahu College, Latur, which is situated in India and one of the greatest college in the India. He is nominated for Shanti Swarup Bhatnagar Prize for the Science and Technology of Indian government in 2014 and 15. With this, I invite Professor Rajesh Mane Sarji for his speech in valedictory session of the international conference. Thank you, sir. Thank you so much. Over to Professor Dr. R.S. Mane, sir.
Namaskar. Thank you very much, Dr. Dasade, sir, for giving a brief introduction about me. The dignitaries on the dais, Dr. Ashok Raoji Shinde, sir, principal of this college, Holani, sir, the convener of this conference, Thomre, sir, co-convener, of course, Dr. Dasade, sir, and many faculty members. At the outset, I am very much thankful for inviting me as a chief guest for this international e-conference on recent trends in nanoscience and nanotechnology, which is organized by Vidnyan Mahavidyalaya, Sangola, and last 2 to 3 days, you people are continuously engaged in. Well, I will talk only for 10 minutes. And I think every new as well as experienced researcher should listen my talk very carefully. Because in Marathi we can call it रात्र वैरेची आहे पण सगळेच वैरी रात्रीत आहेत. Reason behind clear from my side. Research wise, future is very dark and blunt in coming years. Why I'm saying like this? You have heard a lot of talks last 2 to 3 days, nanoscience, nanotechnology. So many eminent personalities have given their talks, like Dr. Patil sir, Suryanshi sir, Butle sir, Shinde sir. Just now, Thomre sir has mentioned about Mane sir and More sir. They are alumni of their colleges. Question is very clear in front of me, how these people have gone ahead. Just now, sir mentioned, Shadari sir mentioned about me. I have done so many achievements. Is it achievement of 1 or 2 days? No, these are not achievements of 1 or 2 days. I spent nearly 25 years of my life in the field of research and development. And then somewhere you can see that Professor Mane achieved top 2% position in the world ranking. Yes, it is possible. But for that, you need to have passion. For that, you need to have the complete plan of work. And for that, you need to dedicate with your hard work. If you don't have these things, you cannot easily achieve your target. Sir has mentioned in his talk that I have achieved so many things in my life. One thing he mentioned, he forgot to mention that in 10th standard, I have only 46% marks that he has not mentioned. The person from farmer family can achieve top 2% position in the world. Why not you? For that, you should be horse of long race. If you think in research, if you can achieve things in one day, it will be very difficult for you, or it will be very impossible for you. So don't expect newcomers, young researchers, don't expect. You will get target in 1 or 2 days. Think yourself after 10 years where you will be, 20 years where you will be, 25 years where you will be, after 50 years where you will be. Your plan of action should be ready in your hand. Scenario is changing drastically. National education policy. Now, the professor or teacher who is not teaching well in the class, nobody will select his subject. As a result of, he will be debarred, or he has to promote elsewhere, or he has to drop down from his service. This is a first threat is coming forward. About job, what I would say, last 12 years, 13 years, government has not recruited any position. And it is open for all. Everybody know that nobody's open. The rate is for 2 crore to 7 crore rupees. Everybody knows that. Nobody's talking about it. It is fact. Where we are going. By doing
Hello, sir. Hello. Hello, sir. Your voice is breaking, sir. I think it is a network problem, sir.
Huh?
Just wait, delegates. Sir will join with.
Sir, am I audible?
Yes, sir. Yes, sir. Yes, sir, please.
I'm extremely sorry. Actually, I don't know where I cut down. But actually, I want to tell you, new researchers. I'm looking at researchers from 20. I will take only 15 minutes to conclude my talk. But this talk is very important for all of you. The young researchers are paying, just I was talking about the barbing system in India and how it is spreading heavily. As I told you, assistant professor to professor or vice chancellor paying 7 crore rupees. And what is intention? With this money, whether you are able to devote yourself? Answer is no, thanks, no. Now, what we can do? We cannot challenge the system. Otherwise, government will come to me, he will pick up me, and it will put up me in jail. Because I'm talking against the system. It's not fair. Because by talking single mega against the system will not change. One example I will give you. In cash promotion, as you know,
Here GD office, the person who is just graduated since before 15 years, he is charging 1 lakh rupees for cash promotion, assistant professor to associate clients, all. This is our system. We cannot change it. What we can do? Thanks. Be a researcher. Research will give you satisfaction throughout the world. Dr. Mori, Dr. Mani, they are in Korea. Why not you? What things are required for that? Money is not required. You should not be rich. You should not be the son of some MLA or police inspector or something like that. Your hard work, passion, attitude will take you to a desired destination. I have seen few talks recently. They're saying, I have prepared this thing, I have prepared that thing. What is use of that to you and society? If I prepare one paper, is it useful to me? You will come to know that. I have, just now, sir has mentioned in his talk, I have more than 400 publications. Believe me, we never cite our own publication. Reason behind is that until and unless it is essentially required, why to cite it? Just about self-satisfaction? By declaring myself as a big scientist, nobody is going to give me Nobel Prize. Intention is clear. Don't call yourself as a big scientist or something different than others. I'm talking for the young smarts. Be passionate. So many opportunities are coming forward. Do research with a keen interest. Publish small articles with full understanding. Don't publish in local journal articles. Don't give reviewers as your friends. Because we know in Marathi, ये आपलीच माणसं आपलीच माती करतात. त्यामुळं in that case you have to give the reviewer external referee. They will check your manuscript very thoroughly and they will give proper inputs for improvement of your article so that other people will cite it. So do research. Go abroad. World is open for you. Instead of giving 14 lakh rupees to these people, give 10 lakh to your own purpose. You will feel the sky is the limit for you for work and development. And if you go there, if you do something, whatever satisfaction you will get, that will be awesome. You can take your parents there. One example, Dr. Nana Shinde, one example is there. Who he was earlier. Just a small person coming from the Pandharpur region, okay, Kurduwadi region. If you would have stayed here, if you stay here, if you go in college, they will first ask you money, they will ask you to do their job, and third, they will not allow you to bring the projects. And even though if you bring the project, they will take money and for only on paper, they will declare our project is over. Like this research you want to do? No. You want to be independent. Research is independent. You should have the capability of handling scientific temperament by yourself. Nobody is going to help you. Friends, sky is the limit for you. Because involved in this national education policy, what is telling you? 40% will be online subject and 60% will be core subject. What will happen if students not select your paper, or if students not select your course, you will be jobless. And after 40, what you will do? Because you don't have ability to do research. So, coming to the conclusion, friends, understand the situation. Focus proper research. Don't do old research. I have seen the zinc oxide paper just now, last presentation I was reading again. We don't understand concept. Zinc oxide prepared, and by doping performance is increasing. We're not asking this question to ourselves, why performance is increasing? If copper is added into zinc oxide, why it is not forming copper oxide? Nobody's asking ourselves. We should understand mechanism, scientific temperament should be with you. If this is happening, why? If it is not happening, why? That kind of understanding you should have with you. And to write small people, you should not be big scientist, but if you write small thing and if you publish in reputed journal, apply abroad. So many opportunities are there, and be a king of your life instead of begging such things for your future. I wish you, everybody, great success. Our SRT University is always open for you if you have passion to research. So far, 500 scholars have shifted abroad for their higher education. Why not you? The person sitting in front of you is a son of farmer. He visited more than 18 countries. Why not you? You make a dream of your life and do question instead of stucking yourself in a nasty place or instead of pressing in dirty place. I wish you all the best. Come forward, sky's the limit, do passionate research, valuable research, publish in reputed journal, and go ahead. People are there to help you. Go ahead. My best wishes are always you. Thank you very much for inviting me as a chief guest. With these few words, I will say thank you very much.
Thank you, sir, for giving your valuable insights on RTNA 2023.
Sir, your voice is unmute, please. You are muted, please unmute. Sir.
Yeah, sorry, sir.
Yeah, your voice was not audible.
Yeah, sir.
Please continue.
I am audible?
Yes, sir.
Yes. Okay. Thank you, sir, for giving your valuable insights on the RTNA 2023. Sir, I am sure your address will help a lot in understanding upcoming research in India. Okay. Thank you, sir. Now we are going to move towards presidential address. I now request to President of this function, Dr. Ashok Rao Shinde, to deliver presidential address.
Hello. Hello, everyone. Hello, sir.
Sir, you are audible and visible. Please.
Okay. Good afternoon, all. Distinguished Chief Guest, Professor R.S. Mane, sir. Dr. B.B. Navle, Head of Department Physics. Dr. S.S. Dasade, IQAC Coordinator, Vidnyan Mahavidyalaya Sangola. Dr. G.V. Thomre, sir, Convener of this conference. Mr. Ashok Kamble, sir, and D.K. Bangar, sir, Member of Organizing Committee, and Honorable Dr. Sikandar Mulani, sir, Principal, Vidnyan Mahavidyalaya Sangola. Most valuable resource person, Dr. C.D. Batula from South Korea, Dr. M.P. Suryavanshi from Sydney, Dr. Mahesh Shinde from US, scientists, research scholars, participants, and staff members. Friends, it's my great pleasure to share presidential remark during valedictory function on Zoom meeting platform in the eve of international conference. Trends in nanomaterial and its applications that in this conference was held between 3rd and 4th May. First of all, I would like to congratulate faculty members of Physics Department for successful organization of such wonderful international events on online platform. And our Physics Department is an innovative department. Every innovative things starts from our Physics Department of Vidnyan Mahavidyalaya Sangola. I am a person from horticulture, so I am very much interested in nanomaterials in horticulture or in agriculture. Agriculture and agriculture food supply management is a complex due to the diverse characteristics in the agriculture products. There are numerous types of horticultural crops and their products, many of which are perishable. In addition, the degree of standardization of some kinds of food products and their management is also still low. In this regard, the potential application of nanotechnology to the horticulture is important. Nanotechnology is also important in sense of biofertilizers, chemical fertilizers like urea and another chemical fertilizers. In last some years, we are going to use huge quantity per acre, but nowadays some grams or some kilograms or grams are sufficient for acres for the horticultural crops and agricultural crops. This is all due to the nanotechnology. Nanosensors are also using in horticulture to identify moisture content in the soil, pesticide residues, nutrient requirement, and crop pest detections. Our chief guest, Honorable Professor R.S. Mane sir, has shared his experience about nanomaterial and its importance in various technological aspects. I read it, today's local newspaper, and details in it. I hope that all participants had enjoyed this conference and very actively participated in this valuable discussion with resource persons. Also, Dr. Sikandar Mulani sir, Principal Vidnyan Mahavidyalaya Sangola, has nicely explained yesterday how the particles in space are responsible for great rainfall situations. Dr. Vatula sir also explains that structural changes in substances are affecting on working capacity of that substances. Friends, all these experiences were very magical. I hope that this conference would to be too much beneficial for our for your basics in research in concern, and every participant had enjoyed this conference. I hope that this conference will definitely add your ongoing academic curriculum in your regular life, and I hope this will further expand your scope of research. I appreciate and thankful to all behalf of Sangola Taluka Shetkari Shikshan Prasarak Mandal Sangola, Vidnyan Mahavidyalaya Sangola, for your participation in this international conference. Wish you all the best, all of you, and thank you. Thank you, sir.
Thank you, sir, for your insightful thoughts. Now, end of the story is the new beginning. On this note, let's conclude a remarkable, memorable, and knowledgeable events. To express words of appreciation and gratitude, I would like to invite Dr. B.B. Nowle for proposing the vote of thanks.
Okay, I am audible?
Yes, you are.
Okay, on behalf of organizing committee of International in Conference on recent trends in nanomaterials and its applications, I feel honored and privileged to get the opportunity to propose a vote of thanks on this valedictory function. Especially, I thanks to our chief guest of this function, Professor Dr. R.S. Mane from Swami Ramanand Tirth, Marathwada University, Nanded, for accepting our invitation and for being here with us. Here with us today. Their thoughts have truly inspired us now today. That will be given by the Mani sir. I would like to thanks to the president of this function, Professor Dr. Ashok Rao Shinde, who is director of Sangola Taluka Shetkari Shikshan Prasarak Mandal, for their constant help to the department, all departments in the college, also valuable guidance and active support for such international event. I would like to thanks to Principal Mulani sir for his support for arranging such international event. I would like to thank to most convener of this conference, Dr. J.V. Thomre, for arranging such a great event. Also, I thanks to IQAC coordinator, Dr. Dasade SS, also Professor Kamble AM, Dr. Dada Sobandgar, Mr. Rajesh Adigle, for their active support. My sincere thanks also goes to all research persons of the all sessions and also all chairpersons who are chair of the all sessions and for giving their valuable knowledge about nanotechnology. Finally, also I thanks to those who give their valuable feedbacks about this conference. Finally, I wish to express my sincere appreciations to all participants. Thank you once again. Have a nice day. Now I over to Kamble AM, sir. Professor Kamble AM.
Okay. the valedictory function is over. Thank you. One note from organizing side. All the participants are requested to please fill up the feedback form, which is given on your WhatsApp group, our WhatsApp group. So this is important note. Thank you, sir.
माने सर आभारी आहे, तुम्ही वेळ दिलात. तुम्ही एक रिसर्च म्हणजे जो मानदंड प्रस्थापित केलाय, तुमचाच फॉलोअप आम्ही घेतोय. आभारी आहे सर.
धन्यवाद सर, आभारी आहे. भेटू सर लवकरच.
माने सर धन्यवाद. आमच्या संस्थेचे डिरेक्टर शिंदे सरांना एक गोष्ट इथं नमूद करू इच्छितो की मी या कॉन्फरन्ससाठी माने सरांना सकाळी 9:10 मेसेज टाकला होता आणि माने सरांचा रिप्लाय 9:14 आला. आय एम रेडी, नोटेड, आय विल बी देअर. म्हणजे मी सगळं नोट केलेलं आहे. तुमच्या कॉन्फरन्सला तुमच्या ठरलेल्या टायमिंगला मी तिथं उपस्थित राहील. इतका सरांनी म्हणजे आपल्या एका मेसेजवरती सरांनी अश्युरन्स दिला होता. तर त्याबद्दल मी सरांचं आपल्या संस्थेचे आणि विज्ञान महाविद्यालय सांगोला या महाविद्यालयाच्या वतीनं मनशा म्हणजे व्यक्तिशः तर आहेच, पण संस्थेच्या वतीनं मी तुमचा आभार व्यक्त करतो सर. धन्यवाद. आणि आम्हाला
शिंदे साहेब बोलतात काहीतरी.
हॅलो माने सर.
बोला सर.
थँक्स टू यू सर.
नाही माय प्लेजर सर. गणपतराव देशमुखांच्या बद्दल बऱ्याच ऐकलेलं आहे साहेब. दुर्दैवानं आम्हाला भेटण्याचा योग आला नाही, पण त्यांच्यातलं 10% जर माझ्या शहरामध्ये तर माझ्या आयुष्यात सार्थक झालं असं समजेन मी.
We are all you call up you offline sir now.
भेटू सर. थँक्यू.
ओके थँक्यू सर.
ओके धन्यवाद. सेशन एंड करा.